Look around you right now. The screen you're watching, the air you're breathing, the chair you're sitting on, even your own body. All of it, every single piece of matter you can see or touch, is made of the same fundamental building blocks, atoms. These incredibly tiny particles, so small that billions of them could fit on the tip of a needle, form the foundation of everything in existence. But have you ever wondered why? Why are atoms the chosen architects of reality? Why not something else? Why do these microscopic spheres of energy hold the secret to building stars that burn for billions of years, planets that harbor life, and complex creatures like us who can ponder their own existence? Tonight, we embark on a journey that will take us from the very beginning of time itself, when the universe was nothing but a hot, chaotic soup of energy, to the present moment, where atoms have organized themselves into the magnificent complexity we see all around us. We'll explore how these simple particles, made of just 3 types of smaller components, can create everything from the delicate petals of a flower to the nuclear furnace at the heart of our sun. The story of atoms is really the story of everything. It's the tale of how order emerged from chaos, how simplicity gave birth to complexity, and how the smallest things in the universe became the building blocks for the largest. From the hydrogen atoms that filled the early cosmos to the carbon atoms that form the backbone of life, these particles carry within them the history of 13.8 billion years of cosmic evolution. As we drift through this exploration together, you'll discover that atoms aren't just random accidents of physics. They represent something far more profound. They are the universe's solution to the problem of existence itself. They are stable enough to persist across cosmic time, yet flexible enough to combine in countless ways. They can share electrons to form the strongest bonds, or give them up entirely to create new partnerships. They can absorb energy and release it as light, allowing us to see the world around us. What makes atoms so special isn't just their structure, but their incredible versatility. A single carbon atom can bond with 4 other atoms, creating the foundation for organic chemistry and life itself. An oxygen atom can share electrons with hydrogen to create water, the solvent that makes life possible. Iron atoms can align their magnetic fields to create the compass needles that guided ancient explorers across unknown seas. But perhaps most remarkably, atoms are universal. The same hydrogen atoms that formed in the first few minutes after the Big Bang are still with us today, cycling through stars, planets, and living beings. The iron in your blood was forged in the nuclear heart of a dying star billions of years ago. The calcium in your bones was created when massive stars exploded in spectacular supernovas, scattering their atomic treasures across the galaxy. This universality means that we are not separate from the cosmos. We are made of it. Every atom in your body is a cosmic immigrant, a traveler that has journeyed across space and time to become part of you. When you look up at the stars on a clear night, you're not just observing distant lights. You're looking at your origins, at the nuclear forges where your atoms were born. As we begin this journey together, let your mind relax and wander through the atomic landscape we're about to explore. We'll visit the moment when the first atoms formed in the cooling aftermath of the Big Bang. We'll journey into the hearts of stars where heavier elements are created through nuclear fusion. We'll discover how atoms learn to dance together, forming the molecules that make chemistry possible and life inevitable. The question of why everything is made of atoms leads us to the deepest mysteries of existence. It touches on the nature of reality itself, the fine-tuning of physical constants that make our universe possible, and the emergence of consciousness from matter. These tiny particles somehow contain within them the potential for everything we know and love. So settle in, close your eyes if you wish, and prepare to explore the atomic foundation of reality. Let the story of atoms carry you through the night, revealing the elegant simplicity that underlies all complexity, the unity that connects all diversity, and the profound truth that in understanding atoms, we come to understand ourselves and our place in the magnificent tapestry of existence. To understand why everything is made of atoms, we first need to explore what atoms actually are. Imagine trying to cut a piece of paper in half, then cutting that half in half again, and continuing this process over and over. Ancient Greek philosophers wondered what would happen if you could keep cutting forever. Would you eventually reach a point where you couldn't cut anymore? They called this smallest possible piece an atom, which means uncuttable in Greek. Today we know that atoms are indeed the smallest units of matter that still retain the properties of an element. But atoms themselves are not solid, indivisible spheres, as the Greeks imagined. Instead, they are mostly empty space, with tiny particles dancing within them in ways that would seem magical to our everyday experience. Picture an atom as a miniature solar system, though this comparison isn't perfect. At the center lies the nucleus, incredibly dense and small, containing almost all of the atom's mass. If an atom were the size of a football stadium, its nucleus would be smaller than a marble sitting at the center of the field. Yet this tiny nucleus contains nearly all of the atom's weight. The nucleus itself is made of two types of particles, called protons and neutrons. Protons carry a positive electrical charge, while neutrons have no charge at all. These particles are held together by one of nature's fundamental forces, the strong nuclear force, which overcomes the natural tendency of the positively charged protons to repel each other. This force is incredibly powerful but works only at extremely short distances, which is why atomic nuclei can remain stable despite containing multiple positively charged particles that would normally push each other apart. The number of protons in a nucleus determines the identity of an element. Hydrogen has 1 proton, helium has 2, lithium has 3, and so on. The number of neutrons can vary even within the same element, creating what we call isotopes. For example, most carbon atoms have 6 neutrons, along with their 6 protons, but some have 7 or 8 neutrons. These different versions of carbon behave almost identically in chemical reactions, but they have slightly different masses and some may be radioactive. Surrounding this dense nucleus is a cloud of electrons, particles that carry a negative electrical charge. But electrons don't orbit the nucleus like planets around the sun. Instead, they exist in what scientists call probability clouds or orbitals. These are regions where electrons are likely to be found, but never in a precise, predictable location. An electron might be here one moment and there the next, existing in a quantum realm where certainty gives way to probability. This quantum behavior of electrons is one of the most fascinating aspects of atomic structure. Unlike the predictable motion of planets or cars, electrons exist in a state of constant uncertainty. We can calculate the probability of finding an electron in a particular region, but we can never know exactly where it is and how fast it's moving at the same time. This isn't due to limitations in our measuring instruments. It's a fundamental property of reality at the atomic scale. What makes atoms truly remarkable is their electrical neutrality. Under normal circumstances, an atom has the same number of electrons as protons. The positive charges of the protons exactly balance the negative charges of the electrons, making the atom electrically neutral overall. This balance is crucial because it allows atoms to interact with each other in predictable ways without being constantly pulled apart by electrical forces. But atoms can lose or gain electrons, becoming electrically charged particles called ions. When an atom loses electrons, it becomes positively charged because it now has more protons than electrons. When it gains electrons, it becomes negatively charged. These charged atoms play crucial roles in many chemical reactions and biological processes. For instance, the salt you sprinkle on your food is made of sodium ions and chloride ions held together by electrical attraction. The electrons in an atom don't all exist at the same distance from the nucleus. They occupy different energy levels or shells, like the floors of a building. The electrons closest to the nucleus are in the lowest energy level and are held most tightly. Those farther away are in higher energy levels and are less tightly bound. This arrangement of electrons in different shells determines how atoms behave chemically and how they bond with other atoms. Think of these electron shells as apartments in a building. The ground floor apartments, closest to the nucleus, are the most desirable and get filled first. As you add more electrons to an atom, they occupy higher floors, farther from the nucleus. Each floor has a limited number of apartments. The first shell can hold only 2 electrons, the second can hold 8, the third can hold 18, and so on. The outermost shell of electrons is particularly important because these are the electrons that participate in chemical bonding. Atoms with incomplete outer shells tend to be reactive, eager to gain, lose, or share electrons to achieve a more stable configuration. It's like people who feel incomplete and are actively looking for relationships. Atoms with complete outer shells, like the noble gases helium and neon, are much less reactive and rarely form chemical bonds under normal conditions. They're like content individuals who are happy being alone. The size of atoms is truly mind-boggling. A typical atom is about 1/10 billionth of a meter across. To put this in perspective, if you could line up atoms side by side, it would take about 25 million of them to stretch across the width of your thumbnail. If atoms were the size of marbles, a marble would be the size of the Earth. Yet despite their incredible smallness, atoms contain vast amounts of empty space. If you could remove all the empty space from the atoms in your body, you would shrink to the size of a grain of rice while still containing all your mass. This mostly empty structure of atoms might seem to make matter fragile and insubstantial, but the opposite is true. The electrical forces between protons and electrons, and the quantum mechanical properties of electrons, create incredibly strong bonds that give matter its solidity and strength. The chair you're sitting on feels solid, not because its atoms are packed tightly together like marbles, but because the electrical forces between atoms create rigid structures that resist being compressed or deformed. Imagine trying to push two magnets together with the same poles facing each other. The invisible magnetic force pushes back, creating a barrier you can feel but not see. Similarly, when you sit in a chair, the electrons in the atoms of your body are repelled by the electrons in the atoms of the chair. This electrical repulsion is what gives matter its apparent solidity. You're not actually touching the chair in the way you might imagine. Instead, you're floating on a cushion of electrical forces. The discovery of atomic structure took centuries of scientific investigation. From ancient Greek philosophy to modern quantum mechanics, our understanding of atoms has evolved dramatically. Scientists like John Dalton proposed that atoms were solid, indivisible spheres. Ernest Rutherford's famous gold foil experiment revealed that atoms have a tiny, dense nucleus surrounded by mostly empty space. Niels Bohr suggested that electrons orbit the nucleus in specific energy levels. Later, quantum mechanics showed us that the reality of atomic structure is even stranger and more wonderful than these early models suggested. Rutherford's gold foil experiment was particularly revealing. He fired tiny particles at a thin sheet of gold, expecting them to pass through with minimal deflection if atoms were solid spheres. Instead, most particles passed straight through, but a few bounced back at sharp angles. It was like firing bullets at tissue paper and having some of them bounce back. This showed that atoms are mostly empty space with a tiny, dense core. Today, we know that atoms themselves are made of even smaller particles. Protons and neutrons are composed of quarks, held together by particles called gluons. The electron appears to be truly fundamental, not made of anything smaller. This subatomic realm reveals layer upon layer of complexity, each level governed by its own physical laws and principles. Quarks come in 6 types with whimsical names like up, down, charm, strange, top, and bottom. They're held together by forces so strong that they can never be separated, even if you put infinite energy into trying to pull them apart. The more energy you use to try to separate quarks, the more new particles you create. It's like trying to cut a rubber band, but instead of cutting it, stretching it creates new rubber bands. This property of quarks means that protons and neutrons can never be broken down into their constituent parts under normal circumstances. What emerges from this complexity is something beautiful and profound. Atoms, despite being mostly empty space and governed by quantum uncertainty, are stable enough to persist for billions of years. They are simple enough to be understood mathematically, yet complex enough to combine in countless ways. They are small enough to be the building blocks of larger structures, yet large enough to carry information and energy. The stability of atoms is remarkable when you consider the forces at play. The nucleus contains positively charged protons that should repel each other violently, yet they're held together by the strong nuclear force. The electrons should spiral into the nucleus due to electrical attraction, yet quantum mechanics prevents this from happening. It's a delicate balance of forces that allows atoms to exist as stable entities. Different elements have different personalities based on their atomic structure. Hydrogen is simple and reactive, eager to bond with other atoms. Helium is noble and aloof, rarely interacting with others. Carbon is versatile and social, able to form complex relationships with many different atoms. Iron is strong and magnetic, able to align with magnetic fields. Gold is noble and unreactive, resistant to corrosion and chemical change. These atomic personalities determine the properties of the materials around us. Diamond is incredibly hard because carbon atoms bond strongly in a three-dimensional network. Graphite is soft and slippery because carbon atoms form sheets that can slide past each other. Water is liquid at room temperature because of the way hydrogen and oxygen atoms bond and interact. The diversity of matter arises from the different ways atoms can combine and arrange themselves. Understanding what atoms are helps us appreciate why they became the universe's chosen building blocks. Their structure gives them the perfect balance of stability and flexibility. They can exist independently as individual elements, or combine with other atoms to form molecules and compounds. They can absorb and release energy, allowing them to participate in the dynamic processes that power stars, drive chemical reactions, and make life possible. The quantum nature of electrons also allows atoms to interact with light in specific ways. When electrons jump between energy levels, they can absorb or emit photons of light with precise energies. This is why different elements produce characteristic colors when heated, why lasers work, and why we can identify the composition of distant stars by analyzing their light. Atoms are also incredibly long-lasting. Most atoms that exist today have been around for billions of years. The hydrogen atoms in your body were created in the first few minutes after the Big Bang. The carbon atoms were forged in the nuclear furnaces of ancient stars. The gold in your jewelry was created in the violent collision of neutron stars. Every atom carries with it a history spanning cosmic time. As we'll discover in our next chapter, atoms weren't always present in the universe. There was a time when the cosmos was too hot and energetic for atoms to exist at all. The story of how atoms formed in the early universe is a tale of cosmic cooling, nuclear physics, and the emergence of the first chemical elements that would eventually give rise to everything we see today. In the beginning, there were no atoms. This might seem impossible to imagine, given that everything around us is made of atoms, but 13.8 billion years ago, the universe was a very different place. It was unimaginably hot, incredibly dense, and filled with energy so intense that atoms simply could not exist. Picture the moment of the Big Bang not as an explosion in space, but as the sudden appearance of space itself, along with time, matter, and energy. In those first fractions of a second, the universe was hotter than the core of any star, denser than the heart of a neutron star, and expanding faster than the speed of light. The temperature was trillions upon trillions of degrees, so hot that not even protons and neutrons could hold together. In this primordial soup, only the most fundamental particles existed. Quarks, the building blocks of protons and neutrons, flew freely through space. Electrons, photons of light, and exotic particles that no longer exist today filled the cosmos. Everything was in constant, violent motion, colliding and transforming in ways that would be impossible under today's cooler conditions. But the universe was expanding and cooling. As space itself grew larger, the energy density decreased, and temperatures began to drop. This cooling was crucial because it allowed the first stable structures to form. About 1 microsecond after the Big Bang, when the temperature had dropped to about 10 trillion degrees Celsius, something remarkable happened. The universe became cool enough for quarks to stick together and form the first protons and neutrons. This process, called quark confinement, was like a cosmic phase transition. Imagine steam condensing into water droplets as it cools. Similarly, as the universe cooled, quarks condensed into protons and neutrons. The strong nuclear force, one of nature's 4 fundamental forces, became dominant at these slightly cooler temperatures and bound quarks together permanently. Even with protons and neutrons now available, atoms still could not form. The universe was still far too hot and energetic. Any attempt by a proton to capture an electron would be immediately thwarted by high-energy photons that would knock the electron away. It was like trying to build a house of cards in a hurricane. The conditions were simply too violent for the delicate balance required to create atoms. For the next few minutes after the Big Bang, the universe continued to cool and expand. When it reached about 100 million degrees Celsius, roughly 10 times hotter than the core of the Sun, the first nuclear reactions began. This period, lasting only about 20 minutes, is called Big Bang nucleosynthesis. and it was during this brief window that the universe created its first atomic nuclei. The process began with the simplest possible nucleus, a single proton, which is the nucleus of hydrogen. But under the extreme conditions of the early universe, some protons began to stick together with neutrons to form more complex nuclei. When a proton and neutron combined, they created deuterium, a heavy form of hydrogen. When two deuterium nuclei collided, they could form helium-4, the most common isotope of helium. These nuclear reactions were incredibly sensitive to the conditions of the early universe. The temperature had to be just right, not too hot to prevent nuclei from forming, but not too cool to stop the reactions entirely. The density of matter had to be precisely balanced to allow collisions between protons and neutrons without being so dense that the reactions would run away and create only heavy elements. During these crucial 20 minutes, the universe manufactured about 75% hydrogen nuclei and 25% helium nuclei, with tiny traces of lithium and beryllium. This ratio of hydrogen to helium would remain essentially unchanged for billions of years and still characterizes the composition of the universe today. It's remarkable that such a brief period in cosmic history determined the fundamental chemical composition of everything that would follow. But even with atomic nuclei now available, complete atoms still could not form. The universe was still too hot, with temperatures of millions of degrees. Any electron that tried to orbit a nucleus would be immediately stripped away by the intense radiation that filled space. The universe was opaque, filled with a dense fog of free electrons and nuclei, with photons of light constantly scattering off the charged particles. For the next 300,000 years, the universe continued its relentless expansion and cooling. During this period, known as the radiation era, light and matter existed in a constant state of interaction. Photons could not travel far before hitting an electron or nucleus and being scattered in a new direction. If you could somehow have been present during this time, you would not have been able to see more than a few inches in any direction, despite the intense brightness everywhere. As the universe cooled toward 3,000 degrees Celsius, still hot enough to melt copper but cool enough for something extraordinary to happen, conditions finally became right for the formation of the first complete atoms. This moment, occurring about 380,000 years after the Big Bang, is called recombination, though it's really the first time that nuclei and electrons combined, rather than recombining. The process of recombination was not sudden but gradual, occurring over tens of thousands of years. As temperatures dropped, electrons began to stick to nuclei, rather than being immediately knocked away. The first atoms were almost entirely hydrogen and helium, the simplest possible atoms with just one or two protons in their nuclei. The formation of these first atoms had a profound effect on the universe. Suddenly, photons of light were no longer constantly scattering off free electrons. Light could finally travel freely through space. The universe became transparent for the first time, transforming from an opaque fog into the clear, star-filled cosmos we recognize today. This moment of first light is still visible to us today. The photons that were released when the first atoms formed have been traveling through space for over 13 billion years, stretched and cooled by the expansion of the universe into microwave radiation. This cosmic microwave background radiation bathes the entire universe and carries with it the imprint of those first atoms. It's like a baby picture of the universe, showing us what conditions were like when atoms first appeared. The early atoms were not distributed perfectly evenly throughout space. Tiny density fluctuations, quantum ripples from the Big Bang itself, meant that some regions had slightly more matter than others. These small variations in density would eventually grow under the influence of gravity to become the large-scale structure we see today, with galaxies, galaxy clusters, and vast cosmic voids. In the denser regions, gravity began to pull hydrogen and helium atoms together, creating the first gas clouds. These primordial clouds were pristine, containing no heavy elements, no carbon, oxygen, or iron. They consisted almost entirely of the hydrogen and helium created in the first few minutes after the Big Bang. The universe had become a place where atoms could exist, but it was still a relatively simple place, lacking the chemical diversity that would later make planets and life possible. The hydrogen atoms that formed during recombination were identical to the hydrogen atoms we know today. Each consisted of a single proton nucleus, orbited by a single electron. These atoms could absorb and emit light at specific wavelengths, creating the first absorption and emission lines in the spectrum of the cosmos. They could also bond with other hydrogen atoms to form hydrogen molecules, the first chemical compounds in the universe. Helium atoms, with their 2 protons and 2 electrons, were more chemically inert. They rarely bonded with other atoms, preferring to remain as isolated, noble gases. This chemical inertness would prove important later, as helium would serve as a reservoir of matter that could be drawn upon when the first stars began to form. The universe at this point was dark, except for the fading glow of the cosmic microwave background. There were no stars yet, no sources of light, other than the gradually cooling radiation left over from the Big Bang. This period is sometimes called the Cosmic Dark Ages, a time when atoms existed but had not yet organized themselves into the brilliant structures that would illuminate the cosmos. But even in this darkness, the stage was being set for the next great chapter in cosmic evolution. Gravity was slowly but inexorably pulling atoms together in the slightly denser regions of space. Over millions of years, these gravitational attractions would grow stronger, eventually leading to the collapse of gas clouds and the formation of the first stars. The creation of atoms during recombination represents one of the most important phase transitions in cosmic history. It marked the end of the radiation-dominated era and the beginning of the matter-dominated era. It was the moment when the universe shifted from being a soup of elementary particles to being a cosmos of atoms, capable of forming complex structures and eventually supporting the chemistry necessary for life. These first atoms carried within them the potential for everything that would follow. The hydrogen atoms would fuel the first stars, providing the raw material for nuclear fusion. The helium atoms would serve as cosmic witnesses, largely unchanged observers of the universe's evolution. Together, they would set the stage for the creation of heavier elements, the formation of planets, and the emergence of life itself. The formation of atoms in the early universe also established the fundamental processes that would govern cosmic evolution for billions of years to come. The balance between gravity trying to pull matter together and thermal energy trying to push it apart would determine the size and structure of stars, galaxies, and galaxy clusters. The ability of atoms to absorb and emit light would make possible the complex feedback mechanisms that regulate star formation and galactic evolution. As we drift through this cosmic story, it's worth reflecting on the remarkable precision required for atoms to form at all. If the universe had expanded too quickly, matter would have been too dilute for gravity to bring atoms together into stars. If it had expanded too slowly, the universe would have collapsed back on itself before atoms could form complex structures. If the ratio of protons to neutrons had been different, we might have ended up with a universe of only hydrogen or only helium, lacking the chemical diversity necessary for complexity. The early universe's creation of atoms represents the cosmos learning how to build stable structures from fundamental particles. It was the first step in a long journey, from simplicity to complexity, from smooth uniformity to intricate organization. In forming atoms, the universe discovered the basic recipe for creating persistent, interacting objects that could serve as the foundation for everything else. As we continue our journey through the story of atoms, we'll next explore how these simple hydrogen and helium atoms became the raw material for the first stars, and how those stars used nuclear fusion to create the heavier elements that would eventually make planets, life, and consciousness possible. The birth of atoms was just the beginning of an even more remarkable story of cosmic chemical evolution. The early universe was a remarkably simple place, chemically speaking. After the first atoms formed during recombination, the cosmos consisted almost entirely of hydrogen and helium, with only the tiniest traces of lithium. While these light elements were sufficient to make the universe transparent and allow gravity to begin sculpting large-scale structures, they lacked the chemical complexity necessary to build rocky planets, organic molecules, or life itself. For hundreds of millions of years, the universe remained in this pristine state. Vast clouds of hydrogen and helium drifted through space, slowly contracting under their own gravity in the regions where matter was slightly more dense than average. These primordial gas clouds were enormous, often containing millions of times more mass than our Sun, and they were destined to become the nurseries where the first stars would be born. The process of star formation in this early universe was a gradual dance between gravity and gas pressure. As hydrogen and helium atoms fell toward the center of these collapsing clouds, they gained speed and kinetic energy. This energy was converted to heat, causing the temperature at the core of the cloud to rise. For millions of years, this gravitational contraction continued, with the central regions growing ever hotter and denser. When the core temperature reached about 10 million degrees Celsius, something extraordinary happened. The hydrogen nuclei, which are simply protons, began moving so fast that they could overcome their mutual electrical repulsion and slam into each other with enough force to stick together. This marked the birth of the first star and the beginning of nuclear fusion, the process that would forge the heavier elements essential for cosmic complexity. Nuclear fusion in stars is like a cosmic alchemy. It takes simple ingredients and transforms them into more complex ones, releasing enormous amounts of energy in the process. The first fusion reaction occurs when two hydrogen nuclei combine to form a deuterium nucleus, releasing a positron and a neutrino. The deuterium nucleus can then fuse with another hydrogen nucleus to create helium-3, which can collide with another helium-3 to produce helium-4 and release two hydrogen nuclei back into the mix. This chain of reactions, called the proton-proton chain, converts hydrogen into helium while releasing the energy that makes stars shine. But even more importantly for our story, it demonstrated that atomic nuclei could be transformed from one element into another. Stars had become the universe's first nuclear laboratories, capable of creating new types of atoms that had never existed before. The first generation of stars was unlike any stars we see today. They were massive giants, often 100 to 200 times more massive than our Sun, burning through their nuclear fuel at prodigious rates. These stellar behemoths lived fast and died young, exhausting their hydrogen fuel in just a few million years, rather than the billions of years that smaller stars like our Sun can sustain fusion. As these massive stars burned through their hydrogen, converting it to helium, they faced an eventual crisis. When the hydrogen in their cores was exhausted, the nuclear fires that had supported them against gravity began to fade. Without the outward pressure from fusion reactions, gravity began to win the eternal struggle, and the stellar core started to contract and heat up once again. But this gravitational collapse led to temperatures even higher than before, hot enough to ignite helium fusion. At about 100 million degrees Celsius, helium nuclei began to collide and stick together in a process called helium burning. 3 helium nuclei can combine in a complex dance to form carbon-12, the first element heavier than helium, to be created in significant quantities in the universe. This carbon creation process, called the triple alpha process, is remarkably sensitive to the fundamental constants of physics. If the strong nuclear force was slightly weaker, helium nuclei wouldn't stick together long enough to form carbon. If it was slightly stronger, all the carbon would immediately combine with more helium to form oxygen, leaving no carbon behind. The fact that this process works at all is one of the remarkable fine-tunings that make complex chemistry possible. With carbon now available, new fusion pathways opened up. Carbon nuclei could capture helium nuclei to form oxygen, the element that would later become essential for life as we know it. Oxygen could capture more helium to form neon, then magnesium, then silicon. Each step required higher temperatures and densities, pushing these massive stars to ever more extreme conditions. As fusion continued, these stellar cores became like nested Russian dolls, with each layer burning a different element. The outermost layer continued burning hydrogen to helium, while deeper layers burned helium to carbon and oxygen, and the innermost regions fused carbon and oxygen into even heavier elements like neon, magnesium, silicon, and sulfur. The creation of elements heavier than carbon opened up an entirely new realm of chemistry. Unlike hydrogen and helium, which can form only the simplest molecules, carbon has the remarkable ability to bond with itself and other atoms in complex chains and rings. Oxygen can form strong bonds with hydrogen to create water, and with carbon to create carbon dioxide. These new chemical possibilities were setting the stage for the rich molecular complexity that would eventually make life possible. The fusion process continued up the periodic table, creating elements like aluminum, phosphorus, sulfur, chlorine, and potassium. Each new element brought new chemical possibilities. Phosphorus would eventually become crucial for storing genetic information in DNA. Sulfur would help proteins fold into their proper shapes. Chlorine would regulate the chemistry of biological fluids. But this nuclear fusion party couldn't continue forever. As stars created heavier and heavier elements, the fusion reactions became less and less energetic. Fusing hydrogen releases a tremendous amount of energy per unit mass, making it an excellent stellar fuel. Fusing helium releases less energy, carbon fusion less still, and so on up the periodic table. When massive stars began fusing silicon into iron, they reached a fundamental limit. Iron has the most stable nucleus of any element, which means that neither fusing it into heavier elements nor splitting it into lighter ones releases energy. Instead, both processes require energy input. When a star's core becomes dominated by iron, it's like a car that has run out of fuel. There's no more nuclear energy available to support the star against its own gravity. What happens next is one of the most spectacular events in the universe. With no energy source to maintain the outward pressure, the iron core collapses catastrophically. In less than a second, a core the size of Earth shrinks to a sphere only about 20 kilometers across, reaching densities comparable to atomic nuclei. The collapse is so violent that it rebounds, sending a shockwave racing outward through the star. This explosion, called a supernova, is so energetic that it can briefly outshine an entire galaxy containing billions of stars. But more importantly for our story, the extreme conditions during a supernova create elements that cannot be formed any other way. The intense neutron flux allows rapid capture of neutrons by atomic nuclei, building up elements heavier than iron, like cobalt, nickel, copper, zinc, and eventually reaching the heaviest naturally occurring elements like uranium. The supernova explosion also serves as the universe's delivery system for heavy elements. All the carbon, oxygen, silicon, iron, and other elements created during the star's life, plus the even heavier elements created during the explosion itself, are blasted into space at speeds of thousands of kilometers per second. These stellar ashes mix with the primordial hydrogen and helium, enriching the interstellar medium with the chemical elements necessary for rocky planets and life. The first supernovas were cosmic watersheds, transforming the universe from a place of simple chemistry to one of unlimited chemical potential. Suddenly, interstellar space contained not just hydrogen and helium, but carbon for building complex molecules, oxygen for creating water and rocks, silicon for forming minerals, and iron for everything from planetary cores to the hemoglobin in blood. These heavy elements didn't just float freely in space. They began to combine with each other, and with hydrogen, to form the first molecules containing heavy elements. Carbon combined with hydrogen to form methane, with oxygen to form carbon monoxide and carbon dioxide. Silicon combined with oxygen to form silicon dioxide, the basis of quartz and sand. Iron atoms began forming tiny grains of metallic iron and iron oxides. The process of element creation in stars established a fundamental pattern that continues today. Stars are nuclear furnaces that transmute light elements into heavy ones, powered by the energy released when smaller nuclei combine into larger ones. The most massive stars live brief, brilliant lives before exploding and scattering their nuclear products throughout the galaxy. Smaller stars burn more slowly and live longer, but they too eventually return their processed material to space. This stellar nucleosynthesis process means that virtually every element in your body, except for hydrogen, was created inside a star. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of these elements were forged in stellar nuclear furnaces billions of years ago. We are literally made of stardust, connected to the cosmos in the most fundamental way possible. The formation of heavy elements also made possible the rich chemistry that characterizes our universe today. With dozens of different types of atoms available, each with its own unique properties, the possibilities for chemical combination became virtually limitless. Atoms could share electrons in covalent bonds, creating molecules with precise shapes and properties. They could transfer electrons in ionic bonds, creating crystals and minerals. They could form metallic bonds, allowing electrons to move freely and creating materials with unique electrical and thermal properties. Different elements brought different chemical personalities to the cosmic stage. Carbon proved to be remarkably versatile, able to form 4 strong bonds with other atoms and create complex 3-dimensional structures. Hydrogen was reactive and lightweight, perfect for forming the backbone of molecular chemistry. Oxygen was electronegative, eager to grab electrons from other atoms and form strong, stable compounds. The chemistry of life itself depends on this stellar heritage. The proteins that catalyze biological reactions rely on precise arrangements of carbon, nitrogen, oxygen, and sulfur atoms. The DNA that stores genetic information uses phosphorus to link its molecular backbone together. The energy currency of cells, ATP, requires phosphorus and nitrogen created in ancient stars. Even the formation of planets depends on stellar nucleosynthesis. Rocky planets like Earth require heavy elements to provide the silicon and iron that form their basic structure. The cores of planets are made largely of iron and nickel, both created in stellar cores. The rocky mantles contain silicon, magnesium, and oxygen, elements forged through nuclear fusion. Without stellar element creation, the universe would contain only gas giant planets made of hydrogen and helium. The process of stellar nucleosynthesis also established the relative abundances of elements that we observe today. Hydrogen remains the most abundant element because it was created in the Big Bang and because stars consume it slowly. Helium is second most abundant, also largely from the Big Bang but supplemented by stellar fusion. Carbon and oxygen are relatively abundant because they're produced efficiently in massive stars. Iron is common because it's the end product of nuclear fusion. Elements heavier than iron are rare because they require the extreme conditions of supernovas to form. This chemical evolution of the universe continues today. Every star that shines is converting hydrogen into heavier elements. Every supernova that explodes enriches the interstellar medium with heavy elements. Each new generation of stars forms from gas that is slightly more enriched with heavy elements than the previous generation, allowing for more complex chemistry and more diverse planetary systems. As we continue our journey through the atomic story, we'll next explore why atoms are so remarkably well suited to be the building blocks of complex structures. Their ability to form chemical bonds, their stability over cosmic timescales, and their quantum mechanical properties all contribute to making atoms the perfect foundation for the intricate architecture of matter that characterizes our universe. Now that we've seen how atoms formed and how stars created the diverse elements that fill our universe, we can begin to understand why atoms became nature's chosen building blocks. What makes atoms so special isn't just that they exist, but that they possess a remarkable combination of properties that makes them perfectly suited for creating the complex, organized structures we see throughout the cosmos. Think of atoms as nature's ultimate construction kit. Unlike the fundamental particles that came before them, such as quarks and electrons, atoms strike the perfect balance between simplicity and complexity. They're simple enough to be stable and predictable, yet complex enough to interact with each other in countless different ways. This balance is what allows atoms to serve as the foundation for everything from the smallest bacteria to the largest galaxies. The first remarkable property of atoms is their incredible stability. Most atoms can persist unchanged for billions or even trillions of years. The hydrogen atoms in your body have existed since the first few minutes after the Big Bang, traveling through space for over 13 billion years before becoming part of you. This longevity is crucial because building complex structures requires components that don't spontaneously change or decay. This stability comes from the quantum mechanical nature of electrons. In the early models of atomic structure, scientists worried that electrons orbiting the nucleus should gradually lose energy and spiral inward, causing atoms to collapse. But quantum mechanics revealed that electrons can only exist in specific energy levels, like steps on a staircase. An electron in the lowest energy level has nowhere lower to go, so it remains stable indefinitely. The stability of atoms also depends on the balance of forces within them. The electromagnetic force holds electrons to the nucleus and prevents atoms from falling apart. The strong nuclear force holds protons and neutrons together in the nucleus despite their electrical repulsion. These forces are precisely tuned to create stable atoms that neither fly apart nor collapse, giving atoms their remarkable persistence through cosmic time. But stability alone wouldn't make atoms special. What truly sets atoms apart is their incredible versatility in forming chemical bonds. Atoms can connect with each other in multiple ways, each creating different types of materials with unique properties. This bonding ability transforms atoms from isolated particles into the interconnected networks that form all the matter around us. The most common type of chemical bond is the covalent bond, where atoms share electrons. When two hydrogen atoms share their electrons, they form a hydrogen molecule that's more stable than either atom alone. When carbon atoms share electrons with four other atoms, they create the complex three-dimensional networks that form diamonds, the hardest natural material known. The same carbon atoms can share electrons in different arrangements to form graphite, which is so soft it's used in pencils. This ability of the same atoms to form completely different materials depending on how they're arranged is one of the most remarkable aspects of atomic behavior. Water and hydrogen peroxide both contain hydrogen and oxygen atoms, but their different arrangements give them vastly different properties. Diamond and graphite are both pure carbon, but their different bonding patterns make one incredibly hard and the other remarkably soft. Atoms can also form ionic bonds by transferring electrons completely from one atom to another. When a sodium atom gives up an electron to a chlorine atom, they become charged ions that attract each other electrostatically, forming sodium chloride or table salt. These ionic compounds often form beautiful crystals with regular, repeating patterns that reflect the underlying organization of their atoms. The third major type of bonding, metallic bonding, occurs when atoms share their electrons in a delocalized sea that flows throughout the material. This creates metals with their characteristic properties. They conduct electricity because electrons can move freely. They're malleable because atoms can slide past each other while maintaining their bonding. And they're lustrous because the mobile electrons can absorb and re-emit light efficiently. What makes atomic bonding so special is that it's governed by relatively simple rules that lead to enormous complexity. The way atoms bond depends primarily on their electron configuration, particularly the electrons in their outermost shell. Atoms with nearly empty or nearly full outer shells tend to form ionic bonds, while atoms with half-filled shells tend to form covalent bonds. These simple rules generate the vast diversity of materials we see in nature. The quantum mechanical nature of electrons also gives atoms another remarkable property. They can exist in multiple bonding states simultaneously until they interact with their environment. This quantum superposition allows atoms to explore different bonding possibilities and settle into the most stable configuration. It's like having a key that can try multiple locks at once until it finds the one that fits perfectly. Atoms also have the remarkable ability to absorb and emit energy in precise, quantized amounts. When an electron jumps from one energy level to another, it can absorb or release a photon of light with a specific energy. This property makes possible everything from photosynthesis, where plants capture solar energy, to the lasers that power our modern technology. It also allows us to identify elements in distant stars by analyzing the specific wavelengths of light they absorb and emit. The size of atoms is another crucial factor in their utility as building blocks. Atoms are small enough that vast numbers of them can work together to create macroscopic objects, yet large enough to carry meaningful information and maintain distinct identities. A single grain of sand contains about 10 to the 18 atoms, each one contributing to the material's overall properties while maintaining its own atomic integrity. This scale also means that atomic interactions are governed by quantum mechanics rather than classical physics, giving atoms access to phenomena that simply don't exist at larger scales. Quantum tunneling allows atoms to overcome energy barriers that should be insurmountable according to classical physics. Quantum entanglement allows atoms to maintain mysterious connections across space. These quantum properties enable chemical reactions that would be impossible in a purely classical world. Atoms also demonstrate remarkable self-organization abilities. Given the right conditions, atoms spontaneously arrange themselves into complex structures without any external guidance. Salt crystals grow with perfect geometric precision. Carbon atoms organize themselves into the elegant hexagonal networks of graphene. Hydrogen and oxygen atoms coordinate their movements to create the flowing networks of liquid water. This self-organization emerges from the relatively simple rules of atomic attraction and repulsion, but it leads to emergent properties that are far more complex than the individual atoms themselves. A water molecule has properties like polarity and hydrogen bonding capability that emerge from the interaction between hydrogen and oxygen atoms, but exist in neither element alone. The diversity of atomic behavior also stems from the quantum mechanical principle that electrons occupy different orbitals with different shapes and orientations. These orbitals determine how atoms can approach each other and form bonds. Some orbitals are spherical, allowing bonding in any direction. Others are dumbbell-shaped, creating directional bonding that leads to specific molecular geometries. Still, others have more complex shapes that enable intricate three-dimensional structures. Carbon exemplifies the special nature of atoms. With 4 electrons in its outer shell, carbon is perfectly positioned to form 4 strong covalent bonds in a tetrahedral arrangement. This gives carbon the ability to create complex three-dimensional networks while maintaining strong, stable bonds. Carbon can form single bonds that allow rotation, double bonds that create rigidity, or triple bonds that store high energy. It can create chains, rings, and branch structures of virtually unlimited complexity. But carbon's versatility goes beyond just forming different structures. It can bond with hydrogen to create hydrocarbons, the basis of fossil fuels and many plastics. It can bond with oxygen to create everything from carbon dioxide to complex carbohydrates. It can bond with nitrogen to create amino acids and proteins, with phosphorus to create the backbone of DNA, and with sulfur to create various biological molecules. The special nature of atoms also lies in their ability to participate in chemical reactions that rearrange their bonding patterns while preserving their individual identities. During a chemical reaction, atoms break some bonds and form new ones, creating new molecules with different properties, but the atoms themselves remain unchanged, ready to participate in further reactions. This allows atoms to be recycled indefinitely through different chemical contexts. Atoms also exhibit what chemists call complementarity, the ability of different atoms to fit together in specific ways that maximize stability and minimize energy. The shapes of atomic orbitals, the distribution of electric charge, and the sizes of atoms all work together to determine which combinations are most favorable. This complementarity is like a three-dimensional puzzle, where pieces can only fit together in certain ways. The temperature dependence of atomic behavior adds another layer of versatility. At low temperatures, atoms move slowly and tend to form ordered structures like crystals. At intermediate temperatures, they have enough energy to flow as liquids while maintaining some organization. At high temperatures, they move rapidly as gases, allowing them to explore different chemical partnerships. This temperature sensitivity allows the same atoms to exist in multiple phases and participate in different types of processes. Atoms also demonstrate remarkable error correction abilities. If an atom finds itself in an unstable configuration, it will generally rearrange to find a more stable state. If a crystal contains defects, atoms will often migrate to repair the structure. If a chemical reaction produces an unstable intermediate, the atoms will continue reacting until they reach a stable final state. This tendency towards stability and error correction helps maintain the integrity of atomic structures over long periods. The magnetic properties of some atoms add yet another dimension to their utility. Atoms with unpaired electrons can act as tiny magnets, allowing them to respond to magnetic fields and interact with each other magnetically. This enables everything from the magnetic storage of information to the magnetic navigation systems used by many animals. Perhaps most remarkably, atoms can carry and process information. The specific arrangement of atoms in a DNA molecule encodes genetic information that can be copied, transmitted, and used to guide the construction of proteins. The positions of atoms in a computer memory chip can represent digital information. The quantum states of atoms can even store and process quantum information in ways that may revolutionize computing. All of these special properties of atoms arise from the fundamental laws of quantum mechanics, electromagnetism, and nuclear physics. But the remarkable thing is how these complex underlying principles give rise to relatively simple rules for atomic behavior that can be understood and predicted. This combination of fundamental complexity and emergent simplicity makes atoms both fascinating to study and practical to use as building blocks. As we continue our exploration of why everything is made of atoms, we'll next discover how these special properties of atoms manifest on the largest scales, making atoms truly universal building blocks that operate the same way throughout the entire cosmos. One of the most profound realizations in science is that atoms are truly universal. The same hydrogen atoms that power the nuclear fusion in distant stars are identical to the hydrogen atoms in the water you drink. The iron atoms forged in stellar cores billions of years ago follow the same quantum mechanical rules, whether they're floating in the vacuum of space, embedded in a rocky asteroid, or flowing through your bloodstream as part of hemoglobin. This universality of atoms represents one of the deepest unifying principles in nature. Across the vast expanse of the observable universe, spanning distances of billions of light years and timescales of billions of years, atoms maintain their fundamental properties and behaviors. A carbon atom behaves the same way in the Andromeda Galaxy as it does on Earth, forming the same types of chemical bonds and following the same physical laws. The evidence for this universality comes from every direction we look in space. When astronomers analyze the light from distant stars and galaxies, they see the same characteristic spectral lines that correspond to the same elements we find on Earth. The hydrogen emission line at a wavelength of 621.7 nanometers appears in the spectra of galaxies billions of light years away, shifted by the expansion of the universe but otherwise identical to what we observe in laboratories. These spectral fingerprints tell us that not only are the same elements present throughout the universe, but they behave according to the same quantum mechanical rules. The precise wavelengths of light absorbed and emitted by atoms depend on the energy differences between electron orbitals, which in turn depend on fundamental constants, like the charge of the electron and Planck's constant. The fact that we see the same spectral lines everywhere confirms that these constants are truly constant across space and time. This universality extends beyond just the presence of elements to their relative abundances. Throughout the observable universe, hydrogen makes up about 75% of normal matter, helium about 24%, and all heavier elements combined constitute only about 1%. This cosmic composition reflects the universal processes of Big Bang nucleosynthesis and stellar evolution that operate the same way in every galaxy. The universality of atoms also manifests in the way they organize themselves into larger structures. Wherever we look in the universe, we see atoms following the same patterns of behavior. In stellar cores, hydrogen atoms fuse into helium under the same conditions of temperature and pressure, regardless of whether the star is in our galaxy or 1 billion of light years away. In planetary atmospheres, molecules form and interact according to the same chemical principles that govern Earth's atmosphere. Even in the most extreme environments in the universe, atoms maintain their fundamental identity while adapting to extraordinary conditions. In the intense magnetic fields around neutron stars, atoms become stretched and distorted, but they remain recognizably the same elements with the same nuclear compositions. In the hearts of gas giant planets where pressures reach millions of times Earth's atmospheric pressure, hydrogen atoms can be compressed into metallic states while retaining their basic atomic structure. The cosmic recycling of atoms provides another dimension to their universality. The atoms in your body have traveled vast distances through space and time before becoming part of you. Some of your hydrogen atoms may have spent millions of years inside a star before being expelled in stellar winds. Some of your carbon atoms might have been part of a distant planet that was destroyed in a supernova explosion billions of years ago. This cosmic journey of atoms means that we're connected to the universe in the most literal sense possible. The calcium in your teeth might have been created in a star that exploded before our solar system even formed. The iron in your blood could have traveled from a galaxy far away, carried by cosmic rays across intergalactic space, before eventually being incorporated into the molecular cloud that gave birth to our sun and planets. The universality of atoms also enables the possibility of life throughout the universe. Because the same chemical elements exist everywhere and follow the same rules of bonding and interaction, the basic chemistry of life could potentially emerge wherever conditions are suitable. Carbon forms the same complex organic molecules on distant exoplanets as it does on Earth. Water molecules have the same unique properties of polarity and hydrogen bonding that make them excellent solvents for biological chemistry. Recent discoveries of organic molecules in space have confirmed that even complex chemistry occurs throughout the universe. Radio telescopes have detected over 200 different molecules in interstellar space, including amino acids, alcohols, and other organic compounds that are essential to life as we know it. These molecules form through the same chemical processes that occur on Earth, demonstrating that atomic behavior is truly universal. The search for exoplanets has revealed that planetary systems are common throughout the galaxy, with many containing rocky planets in the habitable zones where liquid water could exist. The atoms that make up these distant worlds follow the same principles of chemistry and physics that govern our own planet. Silicon and oxygen combine to form the same types of rock-forming minerals. Iron sinks to planetary cores due to the same gravitational and chemical processes. Water molecules exhibit the same unusual property of expanding when they freeze. The universality of atoms also appears in the formation of cosmic structures on the largest scales. Dark matter, though composed of unknown particles, still interacts gravitationally with normal atomic matter in the same way throughout the universe. The formation of galaxies, galaxy clusters, and cosmic filaments follows the same gravitational physics, whether we're looking at nearby structures or ones from the early universe. Even the cosmic microwave background radiation, the afterglow of the Big Bang, carries the imprint of atomic physics. The tiny temperature fluctuations in this radiation reflect the acoustic oscillations in the primordial plasma before atoms formed. These oscillations were driven by the competition between gravity, trying to compress matter, and radiation pressure, trying to expand it, the same physical processes that govern the behavior of matter today. The study of meteorites provides direct evidence for the universality of atomic processes. These fragments of asteroids and other solar system bodies contain the same elements arranged in the same types of minerals we find on Earth. The isotopic ratios of elements in meteorites tell stories of stellar nucleosynthesis and cosmic ray bombardment that occurred billions of years ago, demonstrating that the same nuclear processes operated throughout the early solar system. Comets, often called dirty snowballs, carry pristine samples of the molecular cloud from which our solar system formed. When comets approach the sun and begin to sublimate, they release water vapor, carbon dioxide, methane, and other molecules that formed through the same chemical processes operating in molecular clouds throughout the galaxy. The composition of comet tails provides a direct window into the universal chemistry of space. The universality of atoms extends to their quantum mechanical properties as well. Quantum effects, like tunneling, superposition, and entanglement, operate the same way throughout the universe. These quantum phenomena enable the same types of chemical reactions in distant molecular clouds as they do in terrestrial laboratories. The uncertainty principle places the same fundamental limits on the simultaneous measurement of position and momentum for particles everywhere in the cosmos. Laboratory experiments on Earth can therefore provide insights into processes occurring in the most distant parts of the universe. When scientists study how atoms behave under extreme conditions of temperature, pressure, or magnetic field, they're learning about processes that occur naturally in stellar cores, planetary interiors, and the neighborhoods of black holes. The universality of atomic physics means that Earth-bound experiments can illuminate cosmic phenomena. The cosmic abundance patterns of elements also reflect universal stellar processes. The fact that iron is relatively abundant while gold is extremely rare reflects the universal physics of stellar nucleosynthesis. Elements lighter than iron are created through fusion reactions that release energy, making them common products of stellar burning. Elements heavier than iron require energy input to create, making them rare products of explosive stellar death. The discovery of gravitational waves has opened a new window into the universality of atomic formation. The collision of neutron stars detected by gravitational wave observatories creates the extreme conditions necessary to form the heaviest elements through rapid neutron capture. These cosmic catastrophes occur throughout the universe, enriching galaxies with gold, platinum, uranium, and other heavy elements through the same nuclear processes. The expansion of the universe itself provides evidence for the universality of atomic physics. The rate of cosmic expansion depends partly on the density of matter, which in turn depends on the masses of atoms and their interactions. The fact that the universe expands at the observed rate confirms that atomic masses and fundamental constants have the same values throughout space and time. The cosmic web, the largest structure in the universe, is held together by the gravitational attraction of both dark matter and normal atomic matter. The filaments of galaxies that stretch across hundreds of millions of light years all contain the same mix of hydrogen, helium, and heavier elements, following the same patterns of chemical evolution. This demonstrates that atomic processes operate consistently on the largest observable scales. Climate and weather patterns on exoplanets, where they can be observed, follow the same atmospheric physics that governs Earth's climate. The way water vapor condenses into clouds, how atmospheric circulation transports heat, and how greenhouse gases trap radiation all depend on the universal properties of atoms and molecules. This suggests that atmospheric chemistry operates the same way throughout the galaxy. The magnetic fields of planets and stars arise from the same electromagnetic properties of matter everywhere in the universe. The way charged particles move in magnetic fields, how electric currents generate magnetism, and how magnetic fields interact with plasma all follow Maxwell's equations, regardless of location in the cosmos. This electromagnetic universality enables phenomena like aurora on other planets and magnetic reconnection events in distant stellar coronas. Perhaps most remarkably, the universality of atoms means that consciousness itself might be universal. If life can emerge wherever the right chemical conditions exist, and if consciousness arises from the complex organization of matter, then thinking beings might exist throughout the cosmos, all built from the same universal atoms, following the same physical laws. The profound implication of atomic universality is that we are not isolated inhabitants of a unique corner of the universe, but participants in cosmic processes that operate everywhere and always. Every atom in our bodies connects us to stars we will never see, galaxies we can barely imagine, and cosmic events that occurred long before Earth existed. We are not separate from the universe. We are expressions of its universal atomic nature. As we continue our journey through the story of atoms, we'll next explore how this universal atomic foundation makes possible the emergence of life itself, showing how the same atoms that power stars and build planets can organize themselves into the incredibly complex molecular machinery that characterizes living beings. Of all the remarkable things that atoms can do, perhaps none is more extraordinary than their ability to organize themselves into living beings. Life represents the ultimate expression of atomic creativity, where simple elements combine in intricate patterns to create systems that can grow, reproduce, respond to their environment, and even contemplate their own existence. The story of life begins with just 6 elements that make up 99% of all living matter: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These cosmic gifts from ancient stars possess exactly the right properties to build the molecular machinery of life. Each element brings unique capabilities that, when combined, create possibilities that none could achieve alone. Carbon stands as the central architect of life. With its 4 outer electrons, carbon can form 4 strong bonds, arranged in a perfect tetrahedral geometry. This allows carbon atoms to link together in chains, rings, and complex 3-dimensional networks of virtually unlimited size and complexity. No other element in the periodic table shares this remarkable versatility. Silicon, carbon's closest chemical cousin, forms weaker bonds and prefers simpler structures. Carbon's ability to bond with itself, while also forming strong connections with hydrogen, oxygen, nitrogen, and other elements, makes it the perfect backbone for biological molecules. The carbon atoms in your body tell a story that spans cosmic time. Every carbon atom was forged in the nuclear furnace of a dying star through the triple alpha process, where 3 helium nuclei combine in a delicate dance of nuclear physics. These carbon atoms were scattered into space when massive stars exploded as supernovas, eventually finding their way into the molecular cloud that gave birth to our solar system. After billions of years of cosmic wandering, they became part of you, forming the intricate molecular structures that make your existence possible. Hydrogen, the simplest and most abundant element in the universe, plays crucial supporting roles in the chemistry of life. Hydrogen atoms bond with carbon to form the hydrocarbon backbones of many biological molecules. They bond with oxygen to create water, the essential solvent that makes life's chemistry possible. Perhaps most importantly, hydrogen atoms participate in hydrogen bonds, weak interactions that hold proteins in their proper shapes and allow the 2 strands of DNA to recognize each other. Oxygen brings its own unique properties to the chemistry of life. With 6 electrons in its outer shell, oxygen is eager to gain 2 more electrons to achieve stability. This makes oxygen highly reactive and capable of forming strong bonds with many other elements. Oxygen's electronegativity, its strong attraction for electrons, creates polar molecules like water, that can dissolve other substances and facilitate chemical reactions. Oxygen also serves as the ultimate electron acceptor in cellular respiration, allowing organisms to extract energy from food molecules. Nitrogen, with 5 outer electrons, can form 3 strong bonds and often carries a lone pair of electrons that can participate in chemical reactions. This makes nitrogen essential for building amino acids, the building blocks of proteins and nucleotides, the components of DNA and RNA. The nitrogen cycle, which moves nitrogen atoms between the atmosphere, soil, and living organisms, represents one of the most important biogeochemical processes on Earth. Phosphorus plays a unique role in life's chemistry. Unlike the other major biological elements, phosphorus readily forms multiple bonds, allowing it to link different parts of molecules together. The phosphate groups that form DNA's backbone are made of phosphorus bonded to oxygen atoms. Phosphorus also appears in ATP, the energy currency of cells, where the high-energy bonds between phosphate groups store and release the energy needed for biological processes. Sulfur rounds out the major biological elements with its ability to form disulfide bonds that help stabilize protein structures. The sulfur atoms in the amino acid cysteine can bond with other sulfur atoms, creating crosslinks that lock proteins into their functional shapes. Sulfur also appears in several vitamins and coenzymes essential for cellular metabolism. The magic of life emerges when these elements combine to form the 4 major classes of biological molecules. Carbohydrates, built primarily from carbon, hydrogen, and oxygen, serve as energy sources and structural materials. Simple sugars like glucose provide readily available energy, while complex carbohydrates like cellulose form the structural framework of plants. Lipids, also composed mainly of carbon and hydrogen with some oxygen, create the membranes that separate living cells from their environment. The unique properties of lipid molecules, with hydrophilic heads that interact with water and hydrophobic tails that avoid water, allow them to spontaneously organize into the bilayer membranes that surround every cell. This self-organization represents one of life's most fundamental processes, where simple molecular interactions give rise to complex structures. Proteins represent perhaps the most remarkable achievement of biological chemistry. Built from chains of amino acids linked together by carbon-nitrogen bonds, proteins can fold into an enormous variety of 3-dimensional shapes, each precisely suited to a specific function. Some proteins serve as enzymes, catalyzing chemical reactions with incredible specificity and efficiency. Others provide structural support, transport molecules throughout the body, or defend against foreign invaders. The folding of proteins illustrates the exquisite sensitivity of biological systems to atomic scale interactions. The final shape of a protein depends on weak forces between amino acids, including hydrogen bonds, electrostatic interactions, and hydrophobic effects. Change just one amino acid in a protein chain, and the entire structure may fold differently, potentially altering or destroying the protein's function. This demonstrates how life depends on the precise behavior of individual atoms. Nucleic acids, DNA and RNA, represent the ultimate information storage and processing systems built from atoms. The famous double helix of DNA consists of 2 strands held together by hydrogen bonds between complementary base pairs. Adenine always pairs with thymine, and guanine always pairs with cytosine, because these particular combinations form the optimal number and geometry of hydrogen bonds. This base pairing allows DNA to store genetic information in a code that can be accurately copied and transmitted from one generation to the next. The process of DNA replication demonstrates the remarkable precision of atomic scale machinery. Enzymes called DNA polymerases move along the DNA double helix, reading the sequence of bases and assembling new strands with complementary sequences. This process must be extraordinarily accurate, making fewer than 1 error per billion base pairs copied, because mistakes in DNA replication can lead to harmful mutations. Water deserves special attention as the medium in which life's chemistry occurs. The unique properties of water molecules arise from the way oxygen and hydrogen atoms share electrons. Because oxygen is more electronegative than hydrogen, it pulls the shared electrons closer to itself, creating a partial negative charge on the oxygen and partial positive charges on the hydrogens. This polarity allows water molecules to form hydrogen bonds with each other and with other polar molecules. The hydrogen bonding between water molecules gives water its unusual properties. Water has a high boiling point for such a small molecule, allowing it to remain liquid at the temperatures where life thrives. Water expands when it freezes, making ice less dense than liquid water and allowing it to float, insulating the liquid water below. Water's high heat capacity means it can absorb large amounts of heat with only small temperature changes, helping to stabilize the temperatures in living organisms. Perhaps most importantly, water is an excellent solvent for the polar and ionic molecules that participate in biological chemistry. Salts dissolve in water because the partial charges on water molecules can surround and stabilize the ions. Proteins fold partly to hide their hydrophobic regions from water while exposing their hydrophilic regions. This interaction between biological molecules and water drives many of the processes essential to life. The chemistry of photosynthesis illustrates how atoms power the fundamental processes of life. In the chloroplasts of plants, atoms of magnesium sit at the center of chlorophyll molecules, capturing photons of sunlight and using their energy to drive chemical reactions. Carbon dioxide from the atmosphere combines with water to form glucose, storing solar energy in chemical bonds. This process not only feeds the plant, but also releases oxygen as a byproduct, creating the oxygen-rich atmosphere that supports most life on Earth. Cellular respiration reverses the process of photosynthesis, breaking down glucose and other organic molecules to release their stored energy. This process occurs in the mitochondria of cells, where specialized proteins use the energy released from breaking chemical bonds to create ATP, the universal energy currency of life. The atoms involved in these energy transformations, primarily carbon, hydrogen, and oxygen, cycle continuously between carbon dioxide, water, and organic molecules. The nervous system represents one of the most sophisticated applications of atomic chemistry in living organisms. Nerve cells communicate through electrical signals generated by the movement of sodium, potassium, calcium, and chloride ions across cell membranes. The precise balance of these ions, maintained by protein pumps and channels, allows nerve cells to generate and transmit electrical impulses with incredible speed and precision. Neurotransmitters, the chemical messengers that allow nerve cells to communicate with each other, are complex organic molecules built from the same fundamental atoms as all other biological molecules. Dopamine, serotonin, acetylcholine, and other neurotransmitters affect mood, behavior, and consciousness through their interactions with specific receptor proteins. The fact that consciousness itself may arise from the interactions of atoms represents one of the most profound mysteries in science. The process of evolution depends entirely on the behavior of atoms. Mutations occur when DNA replication makes errors, usually involving the substitution, insertion, or deletion of individual nucleotides. These changes at the atomic level can alter protein structures and functions, sometimes providing organisms with new capabilities that improve their survival and reproduction. Over millions of generations, the accumulation of these atomic scale changes drives the evolution of new species and the incredible diversity of life we see today. The elements required for life are not distributed randomly throughout living organisms. Different tissues and organs concentrate different elements based on their specific functions. Bones concentrate calcium and phosphorus to provide structural strength. Blood contains iron and hemoglobin to transport oxygen. The thyroid gland concentrates iodine to produce hormones that regulate metabolism. This selective concentration of elements shows how life has evolved to make optimal use of the atomic resources available on Earth. Even the aging process reflects the behavior of atoms over time. The accumulation of damage to biological molecules, including DNA, proteins, and lipids, gradually impairs cellular function. Free radicals, highly reactive molecules with unpaired electrons, can damage other molecules through oxidation reactions. Antioxidants work by donating electrons to these free radicals, neutralizing their damaging effects, and demonstrating how life has evolved sophisticated atomic-scale defense mechanisms. The remarkable thing about life is that it achieves such extraordinary complexity using the same atoms that exist throughout the universe. The carbon in your DNA follows the same chemical rules as carbon in a distant galaxy. The hydrogen bonds that hold your proteins together operate according to the same quantum mechanical principles that govern hydrogen everywhere in the cosmos. Life doesn't require exotic matter or special physical laws. It emerges from the ordinary interactions of ordinary atoms under the right conditions. This universality of life's atomic foundation suggests that life could potentially emerge anywhere in the universe where suitable conditions exist. The same elements that make life possible on Earth are abundant throughout the cosmos. The same chemical reactions that power earthly life could occur on distant planets orbiting other stars. While the specific forms that life might take could be vastly different from anything we've seen on Earth, the underlying atomic chemistry would likely be similar. The study of extremophiles, organisms that thrive in extreme environments on Earth, has expanded our understanding of the conditions under which life's atomic chemistry can operate. Some organisms live in boiling water, others in highly acidic conditions, and still others in environments with intense radiation. These discoveries suggest that the atomic basis of life is more robust and adaptable than previously thought, increasing the possibilities for life throughout the universe. As we reflect on the role of atoms in life, we see that living organisms are not separate from the physical universe, but represent its highest expression of organization and complexity. Every breath you take involves billions of atomic-scale machines working in perfect coordination. Every thought you think emerges from the interactions of atoms in your brain. You are not just made of atoms. You are atoms that have learned to think about themselves. In our next chapter, we'll explore the quantum world, where atoms reveal their strangest and most mysterious properties, following rules that defy our everyday intuition, but make possible the very existence of matter itself. As we journey deeper into the nature of atoms, we enter a realm where the familiar rules of everyday experience break down and give way to the strange, counterintuitive laws of quantum mechanics. At the atomic scale, particles behave in ways that would seem impossible in our macroscopic world. Electrons can exist in multiple places simultaneously, atoms can tunnel through barriers that should be impenetrable, and the very act of observation changes the reality being observed. The quantum world isn't some abstract theoretical construct detached from everyday life. It's the fundamental reality that underlies everything we see and experience. The stability of atoms themselves depends on quantum mechanics. Without quantum effects, electrons would spiral into atomic nuclei, atoms would collapse, and matter as we know it simply could not exist. The quantum world is not just strange, it's necessary for our existence. The story of quantum mechanics begins with the puzzle of atomic stability. In the early 1900s, scientists knew that atoms contained negatively charged electrons and positively charged nuclei. According to classical physics, the electromagnetic attraction between these opposite charges should cause electrons to spiral inward, radiating away their energy as electromagnetic waves. This would happen in a tiny fraction of a second, causing all atoms to collapse instantly. But atoms are remarkably stable. The hydrogen atoms in your body have maintained their structure for billions of years without collapsing. This stability was one of the great mysteries that led to the development of quantum mechanics, revealing that nature operates according to fundamentally different rules at the smallest scales. The resolution came with the revolutionary idea that energy comes in discrete packets called quanta. Just as you can't buy half a coin or a fraction of an egg, energy at the atomic scale comes in indivisible units. When an electron absorbs energy, it jumps instantly from one energy level to another, with no gradual transition between states. When it emits energy, it drops from a higher level to a lower one, releasing a photon with precisely the energy difference between the levels. This quantization of energy means that electrons in atoms can only exist in specific allowed states, like a person who can only stand on the steps of a staircase, and never between them. The lowest energy state, the ground state, represents the bottom step. An electron in the ground state has nowhere lower to go, so it remains stable indefinitely. This quantum mechanical principle saves atoms from the classical prediction of collapse and makes the material world possible. But quantum mechanics reveals even stranger aspects of atomic behavior. The position of an electron around an atom is not determined in the way we might expect. Instead of following a definite path like a planet orbiting the sun, an electron exists in what physicists call a probability cloud, or orbital. This cloud represents all the places where the electron might be found if we could somehow measure its position. The shape of these orbitals reflects the quantum mechanical nature of electrons. The simplest orbital, the 1s orbital, is spherically symmetric around the nucleus. The 2p orbitals have a distinctive dumbbell shape, with lobes extending in opposite directions. Higher energy orbitals have even more complex shapes, with intricate patterns of lobes and nodes that reflect the underlying wave nature of electrons. These orbital shapes are not arbitrary but arise from the wave-like properties of electrons. In quantum mechanics, particles like electrons are described by wave functions, mathematical entities that encode all the information about a particle's quantum state. The square of the wave function gives the probability of finding the particle at any particular location, creating the familiar orbital shapes that determine how atoms bond with each other. The wave nature of electrons leads to one of quantum mechanics' most famous principles, the uncertainty principle. Formulated by Werner Heisenberg, this principle states that you cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you determine one property, the less precisely you can know the other. This isn't a limitation of our measuring instruments, but a fundamental feature of reality at the quantum scale. The uncertainty principle has profound implications for atomic structure. It explains why electrons don't simply fall into the nucleus despite their electrical attraction. The closer an electron gets to the nucleus, the more precisely its position is defined, which means its momentum becomes increasingly uncertain. This quantum uncertainty in momentum translates to kinetic energy that keeps the electron from collapsing inward. Quantum mechanics also reveals that particles can exhibit a property called superposition, existing in multiple states simultaneously until they are observed or measured. An electron in an atom can be in a superposition of different energy levels, effectively occupying multiple orbitals at the same time. Only when we make a measurement do we find the electron in one specific state, as if the act of observation forces nature to choose from the available possibilities. This superposition principle enables quantum tunneling, one of the most remarkable quantum effects. In classical physics, a particle needs enough energy to go over a barrier to reach the other side. In quantum mechanics, particles can tunnel through barriers even when they don't have enough energy to go over them. The particle's wave function extends into and beyond the barrier, creating a small but non-zero probability that the particle will appear on the other side. Quantum tunneling plays crucial roles in many atomic processes. In the nuclear fusion reactions that power stars, protons must overcome the electrical repulsion of other protons to get close enough for the strong nuclear force to bind them together. Classically, the protons in stellar cores don't have enough energy to overcome this electrical barrier, but quantum tunneling allows a small fraction of protons to penetrate the barrier and fuse, making stellar nuclear fusion possible and enabling stars to shine. Even the chemical bonds that hold molecules together depend on quantum tunneling. When two atoms approach each other to form a covalent bond, their electron orbitals must overlap. The electrons can tunnel between the atoms, creating a shared electron cloud that binds the atoms together. Without quantum tunneling, the complex chemistry that makes life possible would not exist. Quantum entanglement represents perhaps the most mysterious aspect of quantum mechanics. When two particles interact and then separate, they can remain connected in a way that Einstein famously called spooky action at a distance. Measuring the quantum state of one entangled particle instantly determines the state of its partner, regardless of the distance between them. This connection persists even when the particles are separated by vast distances, seemingly violating our intuitive notions of locality and causality. Entanglement occurs naturally in many atomic processes. When an atom emits two photons simultaneously, those photons are often entangled, sharing correlated properties that persist no matter how far apart they travel. When electrons in atoms change their spin states, they can become entangled with other electrons, creating quantum correlations that influence the atom's chemical behavior. The quantum nature of atoms also manifests in their interaction with light. When an atom absorbs a photon, the energy must exactly match the difference between two atomic energy levels. This creates the characteristic absorption lines in atomic spectra, with each element producing its own unique fingerprint of absorbed wavelengths. Similarly, when atoms emit light, they produce specific wavelengths corresponding to transitions between energy levels. This quantized interaction with light is what makes lasers possible. In a laser, atoms are excited to higher energy levels and then stimulated to emit photons in a coordinated fashion. The emitted photons have identical wavelengths, phases, and directions, creating a coherent beam of light with unique properties. The precise quantum mechanical control of atomic energy states enables technologies from laser surgery to fiber optic communications. Quantum effects also determine the magnetic properties of atoms. Electrons have an intrinsic quantum property called spin, which generates a tiny magnetic field. In most atoms, electrons pair up with opposite spins, cancelling out their magnetic effects. But in some atoms, unpaired electrons create net magnetic moments that allow the atoms to interact with external magnetic fields and with each other magnetically. The Pauli exclusion principle, another fundamental quantum mechanical law, states that no two electrons in an atom can have identical quantum states. This principle explains the shell structure of atoms and the periodic table of elements. As we add more electrons to an atom, they must occupy different orbitals or have different spin orientations, creating the complex electron configurations that determine each element's chemical properties. Quantum mechanics also reveals the probabilistic nature of atomic processes. In classical physics, identical initial conditions always lead to identical outcomes. In quantum mechanics, identical atoms can behave differently when subjected to the same conditions. We can predict the probability of different outcomes, but we cannot predict exactly what will happen to any individual atom. This quantum randomness is fundamental to radioactive decay. An unstable atomic nucleus will eventually decay, emitting particles and transforming into a different element. We can calculate the half-life of a radioactive isotope, the time it takes for half of a sample to decay, but we cannot predict when any particular nucleus will decay. Each nucleus has the same probability of decaying at any given moment, regardless of how long it has already existed. The wave-particle duality of matter represents another central concept in quantum mechanics. Under some circumstances, electrons behave like particles with definite positions and momenta. Under other circumstances, they behave like waves with frequencies and wavelengths. This duality isn't a contradiction, but reflects the limitations of our classical concepts when applied to quantum phenomena. The wavelength of an electron depends on its momentum through the de Broglie relation. Electrons with lower momenta have longer wavelengths, while those with higher momenta have shorter wavelengths. In atoms, the electron wavelengths are comparable to the size of the atom itself, which is why quantum effects dominate atomic behavior. Quantum mechanics also explains why atoms have discrete sizes. The uncertainty principle sets a natural scale for atomic dimensions. If an atom were much smaller, the electrons would be confined to a smaller region, increasing their momentum uncertainty and kinetic energy. If an atom were much larger, the electrons would be farther from the nucleus and less tightly bound. The observed size of atoms represents a quantum mechanical balance between these competing effects. The quantum nature of atoms enables phenomena that have no classical analog. Quantum coherence allows electrons in atoms to maintain phase relationships that persist over time, enabling interference effects between different electron paths. Quantum decoherence explains how quantum systems lose their coherent properties when they interact with their environment, causing them to behave more classically. Modern technology increasingly exploits quantum effects in atoms for practical applications. Quantum computers use the superposition and entanglement properties of atomic systems to perform calculations that would be impossible with classical computers. Atomic clocks achieve unprecedented accuracy by measuring the precise frequencies of atomic transitions. Quantum sensors can detect magnetic fields, electric fields, and gravitational effects, with sensitivities approaching fundamental quantum limits. The study of cold atoms, where temperatures approach absolute zero, has revealed new quantum phenomena that emerge when thermal motion is nearly eliminated. In these extreme conditions, atoms can form exotic states of matter, like Bose-Einstein condensates, where thousands of atoms behave as a single quantum entity. These quantum gases exhibit properties like superfluidity and superconductivity that have no classical explanation. Quantum mechanics also provides insights into the fundamental nature of time and causality at the atomic scale. Quantum processes can exhibit non-local correlations that seem to transcend the normal flow of cause and effect. Virtual particles can briefly violate conservation of energy, popping into existence and disappearing on timescales so short that the uncertainty principle allows these violations. The measurement problem in quantum mechanics raises profound questions about the nature of reality. Before measurement, a quantum system exists in a superposition of all possible states. The act of measurement seems to collapse this superposition into a single definite outcome. But what constitutes a measurement, and how does this collapse occur, remain active areas of research and debate. As we contemplate the quantum world that underlies atomic behavior, we encounter mysteries that challenge our deepest intuitions about reality. Yet these same quantum effects that seem so strange and counterintuitive are absolutely essential for the existence of stable atoms, chemical bonds, and ultimately life itself. The quantum world isn't separate from our everyday experience. It's the hidden foundation that makes our familiar world possible. In our next chapter, we'll explore how our growing understanding of quantum mechanics and atomic behavior is opening new frontiers in technology and science. From quantum computers that could revolutionize information processing to atomic-scale engineering that promises to transform materials, science, and medicine. As our understanding of atoms continues to deepen, we stand on the threshold of a new era where the manipulation of individual atoms and their quantum properties promises to revolutionize technology, medicine, and our fundamental understanding of the universe. The same atoms that have served as passive building blocks for billions of years are now becoming active tools in human hands, opening possibilities that would have seemed like magic to previous generations. The field of nanotechnology represents perhaps the most direct application of our atomic knowledge. Scientists can now manipulate individual atoms with scanning, tunneling microscopes, moving them one by one to create structures with atomic precision. This capability allows us to build materials and devices with properties that emerge directly from their atomic arrangements, rather than relying on the bulk properties of conventional materials. Carbon atoms, with their remarkable versatility, have become the stars of nanotechnology. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, exhibits extraordinary properties that arise entirely from its atomic structure. Despite being only one atom thick, graphene is stronger than steel, conducts electricity better than copper, and is nearly transparent. These properties emerge not from any exotic physics, but simply from the way carbon atoms bond together in a two-dimensional sheet. Carbon nanotubes, formed by rolling graphene sheets into cylinders, display equally remarkable properties. Depending on how the sheet is rolled, nanotubes can be metallic conductors or semiconductors. They can be stronger than any known material while remaining incredibly light. Some nanotubes can carry electrical current without resistance, making them potential components for future electronic devices that operate without energy loss. The discovery of fullerenes, soccer ball-shaped molecules made of 60 carbon atoms, opened an entirely new field of chemistry. These cage-like structures can trap other atoms or molecules inside them, creating potential applications in drug delivery, where therapeutic molecules could be encapsulated and transported to specific locations in the body. The ability to design molecular containers with atomic precision represents a fundamental shift from observing atomic behavior to actively controlling it. Quantum computing represents another frontier where atomic science is reshaping technology. Traditional computers process information using bits that can be either 0 or 1. Quantum computers use quantum bits, or qubits, that can exist in superpositions of both states simultaneously. This quantum parallelism allows quantum computers to explore multiple solutions to a problem at the same time, potentially solving certain types of calculations exponentially faster than classical computers. Individual atoms make excellent qubits because their quantum states can be precisely controlled and measured. Trapped ion quantum computers use lasers to manipulate the energy levels of individual atoms held in electromagnetic traps. The quantum states of these atoms can be entangled with each other, creating the quantum correlations necessary for quantum computation. Each atom becomes a quantum mechanical processing unit, following the same quantum laws that have governed atomic behavior since the beginning of the universe. The challenge in quantum computing lies not in the fundamental physics, which is well understood, but in maintaining quantum coherence long enough to perform useful calculations. Atomic qubits are incredibly fragile, losing their quantum properties when they interact with their environment. Scientists are developing error correction techniques and isolation methods to preserve quantum states, bringing us closer to practical quantum computers that could revolutionize fields from cryptography to drug discovery. Atomic clocks have already achieved precision that seemed impossible just decades ago. These devices measure time by counting the oscillations of electromagnetic radiation emitted by atoms transitioning between energy levels. The frequency of these atomic transitions is remarkably stable, providing a natural standard for timekeeping that far exceeds the accuracy of any mechanical or electronic clock. Modern atomic clocks are so precise that they would gain or lose less than 1 second over the entire age of the universe. This extraordinary accuracy has practical applications in GPS navigation, where timing errors of even nanoseconds would lead to significant positioning errors. As atomic clocks become even more precise, they're enabling new tests of fundamental physics, including searches for variations in fundamental constants and tests of Einstein's theories of relativity. The future of atomic clocks lies in optical atomic clocks that use visible light transitions instead of microwave transitions. These clocks promise even greater precision and may eventually redefine our basic units of time and frequency. Some scientists envision networks of ultra-precise atomic clocks that could detect gravitational waves, map Earth's gravitational field with unprecedented accuracy, or search for dark matter. Atomic-scale engineering is transforming materials science by allowing scientists to design materials with precisely controlled properties. Instead of discovering materials through trial and error or chemical intuition, researchers can now predict and design materials by understanding how their atomic arrangements determine their macroscopic properties. This approach has led to the development of metamaterials with properties that don't exist in nature, such as negative refractive indices that could enable perfect lenses or invisibility cloaks. Single-atom catalysis represents a revolutionary approach to chemical processing. Traditional catalysts use clusters or nanoparticles of metal atoms to accelerate chemical reactions. But scientists have discovered that individual metal atoms dispersed on supports can be even more effective catalysts, using every atom efficiently and enabling new types of chemical transformations. This atomic-level control of catalysis could lead to more efficient production of fuels, pharmaceuticals, and other chemicals, while reducing waste and energy consumption. The field of atomic-scale medicine is emerging as scientists learn to manipulate biological processes at the molecular level. Drug molecules can be designed with atomic precision to interact with specific proteins or enzymes, potentially reducing side effects and improving therapeutic efficacy. Nanoparticles designed at the atomic level can target specific cells or tissues, delivering drugs exactly where they're needed while avoiding healthy cells. Atomic force microscopy and scanning tunneling microscopy now allow scientists to visualize and manipulate individual atoms in living cells. This capability is providing unprecedented insights into biological processes and may eventually enable atomic-level interventions to treat diseases. Scientists can watch individual protein molecules fold, observe DNA replication in real time, and study how cellular machinery operates at the atomic scale. The development of atomic-scale electronics promises to continue the miniaturization trend that has driven the computer revolution. As traditional silicon-based electronics approach their physical limits, researchers are exploring atomic-scale alternatives. Single-atom transistors, molecular electronics, and quantum devices could enable computers that are orders of magnitude smaller and more powerful than current technology. Spintronics, which exploits the quantum spin properties of electrons rather than just their charge, represents another frontier in atomic-scale electronics. By controlling electron spins in atoms and molecules, scientists can create devices that process information in entirely new ways. Spintronic devices could operate faster and use less energy than conventional electronics, while enabling new functionalities like non-volatile memory that retains information without power. Atomic-scale energy technologies are being developed to address global challenges in energy production and storage. Artificial photosynthesis systems use atomic-scale catalysts to split water and produce hydrogen fuel using sunlight, mimicking the fundamental energy conversion process that powers most life on Earth. These systems could provide clean, renewable energy by harnessing the same atomic processes that have sustained life for billions of years. Advanced battery technologies rely on atomic-scale engineering to improve energy storage capacity and charging speeds. By controlling how atoms arrange themselves in battery electrodes and electrolytes, scientists can create batteries that store more energy, charge faster, and last longer. Solid-state batteries use atomic-scale interfaces to conduct ions while preventing dangerous chemical reactions, potentially enabling safer and more efficient energy storage. The exploration of atomic behavior under extreme conditions is revealing new physics and potential applications. Atoms subjected to intense laser fields exhibit highly nonlinear behaviors that could enable new types of light sources and frequency converters. Atoms at ultra-high temperatures and pressures, as occur in stellar cores or laboratory fusion experiments, follow quantum statistical laws that govern the behavior of matter throughout the universe. Cold atom physics, where temperatures approach absolute zero, has become a laboratory for exploring fundamental quantum phenomena. Ultra-cold atoms can form exotic states of matter like Bose-Einstein condensates and degenerate Fermi gases that exhibit macroscopic quantum effects. These systems serve as quantum simulators, allowing scientists to study quantum many-body physics that would be impossible to calculate even with the most powerful computers. Atomic interferometry uses the wave nature of atoms to make incredibly sensitive measurements. Just as light interferometers can detect tiny changes in distance by observing interference patterns, atomic interferometers can detect gravitational fields, accelerations, and rotations with extraordinary precision. These devices could enable new types of navigation systems, geological surveys, and fundamental physics experiments. The study of antimatter atoms is opening new frontiers in fundamental physics. Antihydrogen atoms, made of antiprotons and positrons, should have identical properties to normal hydrogen atoms according to fundamental symmetries in physics. Precise comparisons between matter and antimatter atoms could reveal new physics beyond our current understanding and help explain why the universe contains more matter than antimatter. Atomic-scale archaeology is emerging as scientists develop techniques to analyze ancient materials at the atomic level. Individual atoms in archaeological artifacts can provide information about ancient technologies, trade routes, and environmental conditions. This atomic-level analysis is revealing new details about human history and the development of technology and civilization. The future of atomic science also includes the search for new forms of matter that might exist under conditions we haven't yet achieved. Theoretical predictions suggest the possibility of strange matter, quark matter, and other exotic states that could exist in neutron stars or be created in high-energy particle collisions. Understanding these extreme forms of matter could provide insights into the fundamental nature of atoms and the forces that govern them. Atomic-scale manufacturing, sometimes called molecular manufacturing, envisions the precise construction of complex objects by positioning individual atoms. This technology could enable the production of materials and devices with perfect atomic structure, potentially revolutionizing manufacturing by eliminating defects and waste. While still largely theoretical, advances in atomic manipulation are bringing this vision closer to reality. The integration of artificial intelligence with atomic science is accelerating discovery and enabling new capabilities. Machine learning algorithms can analyze vast databases of atomic properties to predict new materials with desired characteristics. AI-assisted atomic manipulation could enable the construction of complex atomic structures that would be impossible to design manually. Quantum sensing using atomic systems promises to revolutionize measurement science. Individual atoms can serve as extremely sensitive detectors of magnetic fields, electric fields, temperature, and other physical quantities. Networks of quantum sensors could provide unprecedented monitoring capabilities for everything from mineral exploration to medical diagnostics. The development of atomic-scale robots, or nanorobots, could enable new approaches to medicine, environmental cleanup, and manufacturing. These microscopic devices, built from precisely arranged atoms, could operate inside living cells to repair damage, deliver drugs, or monitor biological processes. While still largely conceptual, advances in atomic manipulation and control are making such devices increasingly feasible. Space exploration is beginning to incorporate atomic-scale technologies that could enable new capabilities for spacecraft and space habitats. Atomic-scale materials could provide lightweight, strong structures for spacecraft. Quantum sensors could enable precise navigation in deep space. Atomic-scale manufacturing could enable spacecraft to produce needed materials and components from raw materials found in space. As we look toward the future of atomic science, we see the convergence of our deepest understanding of nature with our most ambitious technological goals. The atoms that formed in the first moments after the Big Bang, that were forged in the hearts of stars, and that self-organized into living beings, are now becoming tools for consciously directed creation and discovery. The future promises atomic-scale control over matter that could address many of humanity's greatest challenges. Clean energy, advanced medicine, powerful computing, and new materials all depend on our growing ability to understand and manipulate atoms. As we continue to probe the quantum nature of atomic behavior, we may discover new physics that opens even more extraordinary possibilities. In our next chapter, we'll explore the fundamental philosophical questions raised by our atomic nature, asking why atoms exist in the forms they do, and what their properties tell us about the deepest nature of reality itself. As we near the end of our journey through the atomic universe, we arrive at perhaps the most profound question of all. We've seen how atoms formed, how they create the elements, how they enable life, and how they follow the strange laws of quantum mechanics. But why do atoms exist in the first place? Why did the universe choose this particular arrangement of matter as its fundamental building block? What is it about the nature of reality itself that makes atoms not just possible, but seemingly inevitable? These questions take us beyond physics and chemistry into the realm of philosophy, where science meets the deepest mysteries of existence. The fact that atoms exist at all, with their precise balance of forces and their remarkable stability, suggests something profound about the underlying structure of reality. The universe could have been organized in countless other ways, yet it chose a path that led to atoms, and through atoms, to complexity, life, and consciousness. Consider the remarkable fine-tuning required for atoms to exist. The electromagnetic force that holds electrons to nuclei must be precisely the right strength. If it were much stronger, electrons would be pulled so tightly to nuclei that chemical bonding would be impossible. If it were much weaker, electrons would barely be bound to atoms, and matter would exist only as a hot plasma of separated charges. The strength of the electromagnetic force appears to be calibrated with extraordinary precision to allow the rich chemistry we observe. Similarly, the strong nuclear force that binds protons and neutrons in atomic nuclei must fall within a narrow range of strengths. If it were significantly stronger, protons would bind together so readily that hydrogen would be rare and only heavy elements would exist. If it were weaker, no elements heavier than hydrogen could form, leaving a universe without the chemical diversity necessary for complex structures and life. The masses of fundamental particles also appear to be finely tuned for atomic existence. The ratio of the proton mass to the electron mass determines the size and properties of atoms. If electrons were much heavier, atoms would be tiny, and chemical bonds would be very different. If protons were much lighter, atomic nuclei would be unstable. The observed masses seem to be precisely calibrated to enable the atomic chemistry we observe. Even the expansion rate of the universe affects the existence of atoms. If the universe had expanded too quickly after the Big Bang, matter would have been too dilute for gravity to form stars and galaxies. Without stars, there would be no nuclear furnaces to create elements heavier than hydrogen and helium. If the universe had expanded too slowly, it would have collapsed back on itself before stars could form and evolve. The expansion rate appears to be precisely tuned to allow cosmic evolution to proceed at the right pace for atoms and complexity to emerge. This apparent fine-tuning of physical constants raises profound questions about the nature of reality. One possibility is that we live in a multiverse, where countless universes exist with different values of fundamental constants. In most of these universes, atoms cannot form, stars cannot shine, and complexity cannot emerge. We observe a universe with atom-friendly constants, simply because we could only exist in such a universe. This anthropic reasoning suggests that our atomic universe is one outcome among many, selected by the requirement that observers like us must exist to observe it. Another possibility is that the fundamental constants are not arbitrary, but are determined by some deeper principle we don't yet understand. Perhaps there is an underlying mathematical structure or physical law that requires the constants to have the values we observe. In this view, atoms are not accidents, but inevitable consequences of the deepest laws of nature. The universe is atomic because it could not be otherwise. The quantum mechanical foundation of atoms also raises deep philosophical questions. Why does nature follow quantum mechanical laws rather than classical ones? The strangeness of quantum mechanics, with its superposition, uncertainty, and entanglement, seems almost designed to make atoms possible. Classical physics would not allow stable atoms, but quantum mechanics provides exactly the right framework for atomic stability and chemical diversity. The role of symmetry in atomic structure suggests another perspective on why atoms are fundamental. The laws of physics exhibit remarkable symmetries that are reflected in atomic properties. The conservation of energy, momentum, and electric charge all emerge from underlying symmetries in the structure of space-time and physical law. These symmetries may be more fundamental than atoms themselves, with atoms emerging as natural consequences of the symmetric structure of reality. The mathematical nature of atomic behavior also points to something profound about the relationship between mathematics and reality. The wave functions that describe electron orbitals, the group theory that explains atomic spectra, and the statistical mechanics that governs atomic ensembles all suggest that mathematics is not just a tool for describing atoms, but is somehow woven into their very existence. This raises the ancient question of whether mathematics is discovered or invented, and whether atoms exist because mathematical relationships are somehow fundamental to reality. The emergence of complexity from atomic simplicity suggests another reason why atoms are foundational. Atoms represent the perfect balance between simplicity and complexity. They are simple enough to be stable and predictable, yet complex enough to combine in virtually unlimited ways. This allows atoms to serve as modules for building more complex structures, from molecules to organisms to technologies. A universe of purely simple particles could not generate complexity, while a universe of inherently complex entities might be too chaotic to form stable structures. The information-carrying capacity of atoms may be another clue to their fundamental nature. Atoms can encode information in their electron configurations, their isotopic compositions, their bonding patterns, and their spatial arrangements. This information can be copied, transmitted, and processed, enabling everything from genetic inheritance to computer memory. Perhaps atoms are fundamental because information processing and storage are fundamental features of reality. The thermodynamic properties of atoms also suggest deep connections to the nature of time and causality. The second law of thermodynamics, which describes the increase of entropy over time, emerges from the statistical behavior of atomic ensembles. The arrow of time itself may be connected to the way atoms and molecules distribute energy and explore phase space. In this view, atoms are not just building blocks in space, but also participants in the fundamental structure of time. The role of atoms in enabling observation and measurement raises questions about the relationship between matter and consciousness. Every observation, every measurement, every thought depends on the behavior of atoms in measurement devices, brains, and nervous systems. Without atoms, there would be no observers to contemplate the universe. This leads to deep questions about whether consciousness is an emergent property of atomic organization, or whether the capacity for consciousness is somehow built into the fundamental nature of matter itself. The universality of atoms throughout the cosmos suggests that they represent a fundamental solution to the problem of organizing matter. Everywhere we look in the universe, from the most distant galaxies to the interior of our own bodies, we find the same atomic elements following the same chemical and physical laws. This universality suggests that atoms are not accidents of local conditions, but fundamental features of how matter organizes itself throughout the universe. The evolutionary perspective on atoms raises intriguing questions about whether atomic properties themselves have evolved. While individual atoms are stable over cosmic timescales, the abundance patterns of elements have changed throughout cosmic history, as stars have converted hydrogen and helium into heavier elements. In some sense, the universe has been exploring the space of possible atomic combinations, discovering new elements and new chemical possibilities over billions of years. The aesthetic qualities of atomic structure also suggest deep connections to fundamental principles. The elegant symmetries of electron orbitals, the beautiful patterns of crystal structures, and the mathematical harmony of atomic spectra all suggest that atoms reflect some underlying aesthetic principle in nature. This connection between beauty and truth has been noted by many physicists, and may point to something fundamental about the relationship between mathematical structure and physical reality. The predictive power of atomic theory provides another perspective on why atoms are fundamental. Once we understand atomic structure and behavior, we can predict the properties of materials, the outcomes of chemical reactions, and the behavior of matter under extreme conditions. This predictive power suggests that atoms capture something essential about the organization of matter, something that reflects deep regularities in the structure of reality. The technological capabilities enabled by atomic understanding demonstrate the practical power of atomic concepts. Our ability to manipulate individual atoms, design materials with atomic precision, and exploit quantum effects for computation all depend on treating atoms as fundamental building blocks. The success of these technologies suggests that the atomic view of matter corresponds to something real and fundamental in nature. The philosophical implications of atomic theory extend to questions about reductionism and emergence. Atoms allow us to understand complex phenomena in terms of simpler components, yet they also enable emergent properties that cannot be predicted from atomic properties alone. This suggests that atoms occupy a special level in the hierarchy of complexity, neither too simple to be interesting, nor too complex to be fundamental. As we contemplate these deep questions about the fundamental nature of atoms, we encounter mysteries that may never be fully resolved. Why does mathematics describe atomic behavior so precisely? Why do the fundamental constants have the values that make atoms possible? Why does quantum mechanics provide the right framework for atomic stability? These questions touch on the deepest mysteries of existence and our place in the cosmic order. Perhaps the most remarkable thing about atoms is that they have enabled the emergence of beings capable of contemplating their own atomic nature. Through billions of years of cosmic evolution, atoms have organized themselves into brains capable of understanding atomic theory, hands capable of manipulating individual atoms, and minds capable of wondering why atoms exist at all. In this sense, atoms are not just the building blocks of matter, but the foundation for consciousness, intelligence, and the capacity for wonder itself. The question of why everything is made of atoms ultimately leads us to reflect on the nature of existence itself. Atoms represent a profound solution to the problem of how to organize matter in ways that enable complexity, stability, information, storage, and ultimately life and consciousness. Whether this solution was inevitable or contingent, designed or accidental, remains one of the deepest mysteries in science and philosophy. In our final chapter, we'll explore how atoms serve as the key to understanding the universe's past, present, and future, and how the atomic perspective reveals the profound interconnectedness of all existence. As we reach the culmination of our atomic journey, we find ourselves face to face with one of the most profound realizations in all of science. Atoms are not merely the building blocks of matter, they are the keys to understanding the grand narrative of the universe itself. From the first moments after the Big Bang to the far distant future, when the last stars fade, atoms serve as both witnesses and participants in the cosmic story that encompasses everything we know and everything we can imagine. The universe's biography is written in atomic language. Every element tells a chapter of this story, from the hydrogen and helium forged in the first few minutes of cosmic time to the heavy elements created in the death throes of massive stars. When we analyze the composition of a distant galaxy, we're reading the history of star formation and stellar evolution across billions of years. When we study the isotopic ratios in meteorites, we're deciphering the nucleosynthetic processes that occurred in the stellar nurseries where our solar system was born. The cosmic abundance of elements serves as a fossil record of the universe's chemical evolution. The fact that hydrogen makes up about 75% of normal matter tells us about the conditions during Big Bang nucleosynthesis, when the universe was hot enough for nuclear reactions but not so hot that complex nuclei would be immediately destroyed. The relative scarcity of lithium compared to theoretical predictions reveals subtle details about the physics of the early universe that we're still working to understand. Each generation of stars has enriched the interstellar medium with heavier elements, gradually increasing the chemical complexity available for planet formation and life. The oldest stars in our galaxy contain almost no elements heavier than hydrogen and helium, reflecting their birth from primordial gas clouds. Younger stars like our Sun show the enrichment from billions of years of stellar nucleosynthesis, containing the carbon, oxygen, silicon, and iron necessary for rocky planets and biological chemistry. This chemical evolution of the universe represents a fundamental transition from simplicity to complexity. The early universe was remarkably uniform, with tiny density fluctuations that would eventually grow into galaxies and galaxy clusters. As gravity amplified these fluctuations and the first stars ignited, the universe began a process of self-organization that continues today. Atoms provided the building blocks for this organization, enabling the formation of increasingly complex structures over cosmic time. The formation of galaxies themselves depends crucially on atomic physics. The ability of hydrogen and helium atoms to cool by radiating away energy allows gas clouds to contract under gravity and form the first stars. Without this atomic cooling, gas clouds would remain too hot to collapse, and star formation would be impossible. The delicate balance between gravitational attraction and thermal pressure, mediated by atomic processes, determines the sizes and structures of galaxies throughout the universe. The cosmic microwave background radiation carries the imprint of the moment when atoms first formed during recombination. The tiny temperature fluctuations in this radiation map reflect the density variations in the primordial plasma just before electrons and nuclei combine to form neutral atoms. These fluctuations, originally quantum mechanical in origin, have been amplified by gravity over billions of years to create the large-scale structure we observe today. Dark matter, though not composed of atoms, plays a crucial role in cosmic structure formation by providing the gravitational scaffolding on which ordinary atomic matter can accumulate. The interplay between dark matter and atomic matter has shaped the evolution of the universe on the largest scales, with atomic matter falling into the gravitational wells created by dark matter and eventually forming the stars and galaxies we observe. The cosmic expansion itself affects atomic behavior in subtle but important ways. As the universe expands, the wavelengths of photons are stretched, cooling the cosmic radiation field. This expansion-driven cooling enabled atoms to form in the first place and continues to affect atomic processes today. The cosmic microwave background, now cooled to just a few degrees above absolute zero, still bathes every atom in the universe in this ancient radiation. The future evolution of the universe is intimately connected to atomic physics. As stars continue to burn hydrogen and create heavier elements, they will gradually deplete the universe's fuel supply. The rate of star formation has already peaked and is now declining as galaxies consume their gas reserves. Eventually, star formation will cease altogether, leaving the universe populated by stellar remnants, white dwarfs, neutron stars, and black holes. The very distant future of atoms themselves is tied to the fundamental stability of matter. Protons, the nuclei of hydrogen atoms, appear to be stable on timescales, much longer than the current age of the universe. But some theories predict that protons may eventually decay, with half-lives of 10 to the 36 years or more. If proton decay occurs, it would represent the ultimate fate of atomic matter, with all atoms eventually disintegrating into lighter particles and radiation. Even if protons are perfectly stable, the expansion of the universe will eventually separate all atoms from each other. In the far future, galaxies will become isolated island universes, no longer able to exchange matter or energy. Within each galaxy, stellar evolution will proceed to its endpoint, leaving behind cold stellar remnants in an increasingly empty and cold universe. Black holes may represent the final chapter in the cosmic story of atoms. These extreme gravitational objects can consume atomic matter, converting it into gravitational energy and hawking radiation. Through black hole evaporation, matter that was once organized into atoms may eventually be converted entirely into radiation, representing the ultimate transformation of the atomic universe. Yet even in this distant future, the quantum mechanical principles that govern atomic behavior will continue to operate. The conservation laws that emerge from fundamental symmetries will remain in effect. The mathematical relationships that describe atomic structure will persist as eternal truths, even if there are no longer any atoms to embody them. The anthropic perspective on atomic physics raises profound questions about our place in this cosmic story. The fact that atoms can form complex structures, support chemical evolution, and enable the emergence of life seems to require a remarkable series of cosmic coincidences. The strengths of fundamental forces, the masses of particles, and the initial conditions of the universe all appear to be precisely tuned to make atomic complexity possible. This apparent fine-tuning has led some to propose that we live in a multiverse, where our observable universe is just one of countless universes with different physical properties. In this view, atoms exist in our universe not because of any underlying necessity, but because we could only exist in a universe where atoms are possible. The vast majority of universes in the multiverse might be sterile, lacking the conditions necessary for atomic complexity and life. Alternatively, the apparent fine-tuning might reflect deeper principles that we don't yet understand. Perhaps the fundamental constants are not arbitrary parameters, but are determined by some underlying mathematical structure or physical principle. In this view, atoms exist because they represent inevitable solutions to fundamental equations that govern the structure of reality. The search for a theory of quantum gravity may provide insights into why atoms exist and why they have the properties we observe. Such a theory would unify our understanding of the quantum mechanical world of atoms with the gravitational physics that governs cosmic structure. It might reveal that atomic properties are determined by the geometry of space-time itself, or by relationships between quantum mechanics and gravity that we don't currently understand. String theory and other approaches to quantum gravity suggest that the familiar three-dimensional space we observe may be just one aspect of a higher dimensional reality. In these theories, the properties of atoms might be determined by the way higher dimensional structures project into our three-dimensional world. The elegant mathematical structure of atomic theory might reflect deeper geometric principles operating in dimensions we cannot directly perceive. The holographic principle, emerging from black hole physics, suggests that the information content of any region of space is encoded on its boundary. This principle might have implications for understanding how atomic information is stored and processed, and how the microscopic degrees of freedom of atoms relate to macroscopic properties of matter. Quantum field theory, the framework that unifies quantum mechanics with special relativity, reveals atoms to be excitations in underlying quantum fields that fill all of space. In this view, atoms are not fundamental objects, but are manifestations of deeper field structures. The electron is an excitation of the electron field, the photon is an excitation of the electromagnetic field, and so on. This perspective suggests that atoms emerge from a more fundamental level of reality based on quantum fields and their interactions. The discovery of the Higgs boson and the Higgs field has revealed how particles acquire mass through their interactions with fields that permeate space. This mechanism might provide clues about why atoms have the masses and properties they do, and how these properties emerge from more fundamental field interactions. Dark energy, the mysterious force driving the accelerated expansion of the universe, represents one of the biggest puzzles in modern cosmology. Understanding dark energy might provide insights into the ultimate fate of atoms and the universe as a whole. If dark energy continues to drive accelerated expansion, it could eventually overcome all other forces, leading to a big rip scenario where atoms themselves are torn apart. The study of cosmic inflation, the hypothetical period of rapid expansion in the early universe, might explain the initial conditions that made atomic formation possible. Inflation could explain why the universe is so uniform on large scales, while still containing the tiny fluctuations that eventually grew into galaxies. Understanding inflation might reveal why the universe has exactly the right properties to support atomic complexity. The nature of time itself remains one of the deepest mysteries in physics. Atoms exist in time, undergoing transitions between quantum states and participating in chemical reactions. But the fundamental nature of time, whether it emerges from more basic principles or is truly fundamental, remains unclear. Understanding the relationship between time and atomic processes might provide insights into both the nature of time and the role of atoms in the cosmic order. Consciousness represents perhaps the most mysterious aspect of the atomic universe. The fact that atoms can organize themselves into brains capable of understanding atomic theory, contemplating the cosmos, and experiencing subjective awareness remains one of the greatest puzzles in science. Whether consciousness is an emergent property of complex atomic arrangements or reflects something more fundamental about the nature of matter and information remains an open question. The possibility of artificial consciousness raises questions about whether consciousness is unique to biological atomic arrangements or could emerge from other types of atomic organization. If consciousness can exist in artificial systems, it might suggest that the capacity for awareness is a more general property of complex atomic information processing systems. The search for extraterrestrial life represents an attempt to understand whether the atomic basis of life is universal. If life emerges wherever atomic chemistry permits, it would suggest that the emergence of complexity and consciousness is a natural outcome of atomic evolution. If life is rare or unique to Earth, it might indicate that the transition from atomic chemistry to living systems requires extraordinary circumstances. The cosmic perspective reveals that we are not separate from the universe, but are expressions of its atomic nature. Every atom in our bodies was forged in stellar cores, or in the Big Bang itself. We are literally made of stardust, sharing a material heritage with every other structure in the cosmos. This connection means that understanding atoms is not just understanding matter, it's understanding ourselves and our place in the cosmic story. The mathematical beauty of atomic theory suggests deep connections between mind and cosmos, between the abstract realm of mathematics and the physical world of atoms. The fact that human minds, themselves made of atoms, can comprehend the mathematical laws that govern atomic behavior hints at a profound harmony between consciousness and cosmos that we are only beginning to appreciate. As we contemplate the mystery of the atomic universe, we encounter questions that touch on the deepest aspects of existence. Why does anything exist at all? Why do the laws of physics have the form they do? Why is the universe comprehensible to minds made of atoms? These questions may never be fully answered, but they remind us that atoms are not just building blocks of matter, but participants in the greatest mystery of all the existence and nature of reality itself. In our final reflection, we'll consider the quiet beauty of atoms and how this atomic perspective can bring us peace, wonder, and a sense of connection to the magnificent cosmos of which we are a part. As our journey through the atomic universe draws to a close, we find ourselves in a place of quiet wonder. We began with a simple question: why is everything made of atoms? And we have traveled through cosmic time and quantum space to discover that atoms are far more than just building blocks. They are the universe's solution to the problem of existence itself, the perfect balance between simplicity and complexity that makes everything possible, from the smallest virus to the largest galaxy, from a grain of sand to a human thought. In the gentle darkness of this moment, let yourself feel the profound connection that atoms create between you and everything that exists. The oxygen atoms you're breathing right now were created in the nuclear furnace of a massive star that lived and died billions of years ago. The carbon atoms in your DNA were forged in stellar cores through the delicate triple alpha process, a cosmic dance of nuclear physics that seems almost choreographed to make life possible. The calcium atoms in your bones were scattered across space in the spectacular explosion of a supernova, traveling through the galaxy for eons, before finding their way into the molecular cloud that gave birth to our solar system. The iron atoms flowing through your bloodstream carry the signature of cosmic violence and cosmic creation, bearing within them the history of stellar death and stellar birth that has shaped our universe for over 13 billion years. Every breath you take connects you to every other living being that has ever existed. The atoms cycling through your lungs have been part of countless other organisms throughout Earth's history. They have been in the leaves of ancient forests, the bodies of dinosaurs, the first simple cells that learned to harness sunlight, and the complex brains of every human who has ever contemplated the night sky. You are not separate from life on Earth. You are a temporary arrangement of atoms that have been alive in countless forms for billions of years. The hydrogen atoms in the water in your body are even more ancient, created in the first few minutes after the Big Bang, when the universe was young and simple. These atoms have witnessed the entire history of cosmic evolution, from the formation of the first stars to the emergence of galaxies, from the birth of our solar system to the evolution of life on Earth. They carry within them the memory of a time when the universe was nothing but hot plasma and the dream of everything that would eventually become possible. As you rest here in the darkness, surrounded by the quiet presence of countless atoms, consider the remarkable fact that these invisible particles are not truly invisible at all. They reveal themselves in every sensation you experience. The warmth you feel comes from the motion of atoms. The softness of your pillow reflects the way atoms arrange themselves in materials. The air you breathe exists because atoms can form molecules that remain gaseous at the temperatures where life thrives. The light that illuminated your day was created by atoms in the sun's core, where hydrogen nuclei overcome their electrical repulsion to fuse together, releasing the energy that has powered life on Earth for billions of years. Even in darkness, atoms continue their silent work. In your body, cellular processes continue as atoms rearrange themselves in the chemical reactions that sustain life. In the world around you, atoms slowly shift and change, participating in the gradual evolution of matter that has been ongoing since the universe began. The remarkable thing about atoms is their eternal nature combined with their constant change. The atoms themselves persist across cosmic time, but their arrangements are endlessly creative. The same carbon atom might spend millions of years as part of a limestone rock, then become dissolved in the ocean, incorporated into a living organism, released as carbon dioxide, and eventually become part of a new living being. Atoms are both permanent and impermanent, both stable and dynamic, both simple and infinitely complex in their combinations. In the quantum realm where atoms exist, the familiar boundaries between separate objects become blurred. Electrons can tunnel through barriers, existing in multiple places simultaneously until observed. Atoms can become entangled across vast distances, sharing properties in ways that transcend our ordinary understanding of space and time. At the deepest level, the atomic world reveals that separation is an illusion, that everything is connected through invisible quantum threads that bind the universe into a unified whole. The beauty of atoms lies not just in their complexity, but in their simplicity. Despite being composed of multiple particles following quantum mechanical laws, atoms behave in ways that can be understood, predicted, and even controlled. The periodic table represents one of science's greatest achievements, organizing all atomic behavior into elegant patterns that reflect deeper symmetries in nature. Each element has its own personality, its own chemical preferences, its own role to play in the cosmic story. The universality of atoms means that you are connected not just to life on Earth, but to the entire cosmos. The same physical laws that govern the atoms in your body also govern the atoms in distant galaxies. The same quantum mechanical principles that make your thoughts possible also operate in the cores of neutron stars and the atmospheres of exoplanets. You are not an isolated being in an alien universe. You are a conscious expression of the same atomic processes that shape everything from the smallest molecules to the largest cosmic structures. This atomic perspective brings a unique form of peace. Your worries, your fears, your daily concerns are real and important, but they exist within a larger context of cosmic time and atomic permanence. The atoms that make you who you are have existed for billions of years and will continue to exist for billions more. You are both a temporary arrangement and a permanent participant in the ongoing story of the universe. The fact that atoms can organize themselves into beings capable of understanding atomic theory represents one of the universe's most remarkable achievements. Through billions of years of cosmic evolution, atoms have learned to think about themselves. They have formed brains that can contemplate their own quantum nature, hands that can manipulate individual atoms, and minds that can wonder about their place in the cosmic order. In understanding atoms, we understand ourselves. In manipulating atoms, we participate in the same creative processes that have shaped the universe since its beginning. As you drift towards sleep, let the atomic world envelop you with its quiet certainty. You are not falling asleep alone. You are surrounded by the company of countless atoms, each one a tiny universe following quantum laws that connect you to everything that has ever existed or ever will exist. The electrons in your brain are settling into lower energy states, the molecules in your muscles are slowing their vibrations, and the atoms throughout your body are preparing for the restorative processes of sleep. In your dreams tonight, you might visit distant worlds where the same atoms that compose you also form alien landscapes and exotic life forms. You might journey backward in time to witness the formation of the elements in stellar cores, or forward to see how atoms will continue to organize themselves into unimaginable forms of complexity and beauty. These dreams are not fantasies but reflections of the deep truth that atoms make everything possible and everything connected. The morning will bring new challenges and new experiences, but they will all be built from the same atomic foundation that has supported every moment of your life and every moment in the history of the universe. The atoms in your breakfast will provide energy through the same chemical processes that power stars. The atoms in your brain will process information using the same quantum mechanical principles that govern all of reality. Rest now in the knowledge that you are part of something infinitely larger and more beautiful than any individual concern or worry. You are a conscious arrangement of stardust, a thinking pattern of ancient atoms, a temporary but precious expression of the universe's capacity for awareness and wonder. The atoms that make you possible have traveled across cosmic time and space to be exactly where they are, participating in the magnificent complexity of your existence. Let the quiet beauty of atoms fill your awareness as you transition towards sleep. Feel the profound connection between your consciousness and the quantum world that underlies all reality. Know that in understanding atoms, you have touched something eternal and universal, something that connects you to the deepest mysteries and the most profound beauties of existence. The universe is not vast and empty, but intimate and full, populated everywhere by atoms following the same elegant laws, creating the same endless possibilities for complexity, beauty, and wonder. You are not a stranger in this atomic universe. You are its most remarkable achievement, a configuration of matter that has learned to appreciate the very atoms from which it is made. Sleep well, knowing that every atom in your body is a messenger from the stars, carrying within it the history of cosmic creation and the promise of infinite possibility. In your dreams, let yourself explore the atomic landscapes of imagination, where quantum mechanics meets consciousness, and where the smallest building blocks of reality reveal themselves to be the foundations of everything magnificent and meaningful in existence. Tomorrow will bring new atomic adventures, new opportunities to participate in the ongoing creativity of the universe, new chances to marvel at the extraordinary fact that atoms, simple though they are, make possible everything we know and love. Rest now beneath the stars, knowing that you and they are made of the same atomic elements, following the same physical laws, participating in the same cosmic story that began with the Big Bang and continues through every moment of your existence. The quiet beauty of atoms surrounds you, supports you, and connects you to everything that has ever been or ever will be. In this atomic universe, you are never alone, never separate, never disconnected from the magnificent whole of which you are an essential and irreplaceable part.